If you like the space and learn about its curiosities, consider subscribing to the channel. Thank you for your attention and enjoy the video. Neutron stars are some of the most incredible objects in the universe, possessing characteristics that stretch the limits of what we know about physics and space. They form when massive stars undergo a supernova explosion, collapsing under their own gravity to a point so dense that they challenge our understanding of matter. These cosmic remnants may be only about 20 kilometers in diameter, yet they carry more mass than our Sun, making them unimaginably dense. Just a teaspoon of neutron star material would weigh around 6 billion tons on Earth. This almost unimaginable density is due to their composition. The core collapse of a dying star packs protons and electrons so tightly that they fuse into neutrons, creating a star almost entirely made of neutrons, the building blocks of atomic nuclei. Neutron stars also spin at astonishing rates, sometimes rotating hundreds of times per second. When a neutron star forms, it retains the angular momentum of its parent star, causing it to spin faster as it shrinks. This rapid rotation can give rise to a phenomenon known as a pulsar. Pulsars are neutron stars that emit beams of electromagnetic radiation from their magnetic poles. If these beams point toward Earth, we can detect them as regular pulses like a cosmic lighthouse. Pulsars are so precise that they rival atomic clocks, allowing astronomers to use them to measure time and distances across the galaxy with exceptional accuracy. Another astonishing feature of neutron stars is their magnetic fields. The magnetic field of a neutron star can be trillions of times stronger than Earth's, making them some of the most magnetized objects in the universe. In some cases, the magnetic fields are so intense that they can distort the shapes of atoms themselves. These magnetic fields can also lead to the creation of magnetars, a type of neutron star with an even more extreme magnetic field. Magnetars occasionally release powerful bursts of gamma rays and X-rays, creating bursts that are sometimes detectable from across the galaxy. If one of these bursts were to occur close to Earth, it could theoretically affect satellites and even some electronic devices. Temperature is another area where neutron stars push the boundaries. When they first form, neutron stars are incredibly hot, reaching temperatures of up to 1 billion degrees. Over time, they cool, but they remain hot enough to emit X-rays detectable from Earth. This intense heat results from the gravitational energy released as the core of the dying star collapses. One of the most mysterious aspects of neutron stars is the possibility of an exotic state of matter in their core. Some scientists believe that the immense pressure inside neutron stars might create conditions where quarks, the fundamental particles that make up protons and neutrons, become deconfined and can move freely. This hypothetical substance, known as quark matter, would represent a new state of matter, unlike anything we have seen on Earth. Studying neutron stars provides scientists with clues about how matter behaves under the most extreme conditions in the universe. Neutron stars are also crucial to our understanding of gravity. As highly dense objects, they create intense gravitational fields that warp the space-time around them. This warping can cause gravitational waves, ripples in space-time, when two neutron stars collide. These collisions are so energetic that they can produce elements like gold and platinum, dispersing them across the cosmos. In 2017, scientists detected gravitational waves from a neutron star collision, marking a groundbreaking moment in astrophysics. This observation confirmed not only the existence of gravitational waves from neutron stars, but also that such collisions are a cosmic source of some of the heaviest elements we know. The study of neutron stars continues to reveal new insights into the laws of physics. They are natural laboratories for studying nuclear physics, quantum mechanics, and general relativity, all within a single object. Neutron stars push us to rethink the limits of matter, energy, and even our understanding of the fundamental forces that govern the universe. Their extreme characteristics make them a fascinating focus for astronomers and physicists alike, with each discovery providing a window into the strange and often counterintuitive nature of the cosmos. In a universe filled with wonders, neutron stars stand as some of the most extreme and enigmatic entities, reminding us just how much there is yet to learn about the nature of space and time. The next incredible detail about neutron stars lies in their gravitational effects, which are nothing short of mind-bending. Despite their relatively small size, neutron stars pack so much mass into such a tiny space that they create gravitational fields billions of times stronger than Earth's. This extreme gravity doesn't just hold the star together, it distorts the very fabric of space-time around it. The gravitational pull is so strong that it bends light, allowing us to see parts of the star's surface that should be hidden from view. This phenomenon, known as gravitational lensing, creates a surreal visual effect, making the neutron star appear larger and even more otherworldly. Neutron stars also contribute to one of the rarest phenomena in the cosmos, the kilonova. When two neutron stars spiral together and finally collide, they release an enormous amount of energy. This cataclysmic event generates a burst of gravitational waves, detectable on Earth, and produces an explosion so bright it rivals the light output of an entire galaxy. Unlike regular supernovae, which mostly produce lighter elements, a kilonova is rich in heavy elements like gold, platinum, and uranium. This process explains how some of the heaviest and rarest elements in the universe are formed, eventually seeding the cosmos with the raw materials needed to create planets, moons, and even life itself. And yet, not all neutron stars remain isolated in the void of space. Some find themselves in binary systems, orbiting around another star. In these cases, the neutron star's gravity often pulls matter from its companion, forming an accretion disk around it. This disk of hot, swirling gas gradually spirals inward, heating up to millions of degrees and emitting intense X-rays. These X-ray emissions can be observed from Earth, providing astronomers with insights into the dynamics of mass transfer and high-energy processes near neutron stars. These X-ray binaries are among the brightest objects in the X-ray sky and serve as a key observational window into the universe's most extreme environments. Scientists also hypothesize that under specific conditions, a neutron star can even transform into a black hole. If a neutron star continues to gain mass, either by pulling material from a companion star or merging with another neutron star, it may eventually reach a critical mass limit. When this threshold is exceeded, not even the neutron degeneracy pressure that supports the star can withstand the gravitational collapse, and the neutron star is crushed further into a black hole. This transformation represents one of the few direct paths from ordinary matter to a black hole, highlighting the neutron star's role as a pivotal bridge between different states of matter and phases of stellar evolution. One particularly fascinating idea is that some neutron stars could harbor a layer of nuclear pasta beneath their crust. As neutron stars cool, the extreme pressures inside may force neutrons and protons to arrange themselves in unique shapes, like sheets, tubes, or clumps, resembling different forms of pasta. These formations are thought to be incredibly strong, potentially making nuclear pasta the hardest known material in the universe. Its bizarre structure, which results from the interplay of nuclear forces under unimaginable pressure, is a compelling example of how matter behaves under conditions far beyond anything we can recreate on Earth. Adding to the mystery of neutron stars, some may possess glitches. These are sudden changes in their rotation rate, which appear as minor jumps in their otherwise consistent spin. Glitches are believed to be caused by interactions within the neutron star's interior, where the superfluid core momentarily transfers angular momentum to the crust. This sudden exchange of energy can alter the star's rotation speed slightly. Observing and analyzing these glitches allows scientists to study the mysterious internal structure of neutron stars, offering clues about the behavior of superfluids and the forces at play inside these dense objects. Neutron stars, with their dense, spinning, and highly magnetic nature, may also emit jets of particles at nearly the speed of light. These jets, powered by the intense magnetic fields and rapid rotation, shoot out from the magnetic poles of the neutron star. If these jets align with Earth, we observe them as pulses of radiation, creating a cosmic heartbeat effect. Each pulse marks a rotation, creating a rhythm that can be used to track time across space. In fact, pulsars are so reliable in their timing that they have been considered as potential cosmic beacons for future interstellar navigation, offering a celestial map of consistent pulses that can guide spacecraft through the galaxy. Even though neutron stars are considered dead stars, they often exhibit bursts of lifelike activity, including powerful X-ray bursts. In binary systems, if a neutron star captures material from its companion, it can create a temporary buildup of nuclear fuel on its surface. Eventually, this fuel layer ignites in a thermonuclear explosion, releasing massive amounts of energy in a matter of seconds. These bursts can shine as brightly as 1,000,000 suns for a short period, illuminating the neutron star and the space around it. By studying these bursts, astronomers can glean information about nuclear reactions and the properties of matter at extremely high densities. In the quest to understand neutron stars, scientists continue to explore the possibility of even stranger types of stars. One example is the hypothetical quark star, which could exist if the core of a neutron star collapses into a state where quarks, the fundamental building blocks of protons and neutrons, are free to move independently. This exotic matter would create an even denser state, potentially giving rise to new types of stars and leading us closer to understanding the fundamental building blocks of matter. Another remarkable characteristic of neutron stars is their potential to exhibit starquakes, a phenomenon similar to earthquakes on Earth, but vastly more powerful. Starquakes occur due to the intense stress and strain within the star's crust, caused by its immense gravitational field and rapid rotation. As the crust of the neutron star adjusts to these forces, it can crack, releasing a burst of energy in the form of X-rays or gamma rays. These starquakes can be so powerful that they briefly outshine entire galaxies, sending shockwaves of energy across space. Studying these bursts offers scientists clues about the structure of neutron stars and the composition of their crust, which remains one of the greatest puzzles in astrophysics. One of the most intriguing mysteries of neutron stars is their role in creating fast radio bursts, FRBs. These are incredibly short but powerful bursts of radio waves that last only a few milliseconds, yet emit as much energy as our sun does in an entire day. While the exact origins of FRBs are still unknown, some scientists believe that neutron stars, especially magnetars, could be responsible. Magnetars, with their extreme magnetic fields, could produce these bursts during periods of intense magnetic activity. As the magnetar's magnetic field twists and realigns, it could release massive amounts of energy in the form of a radio pulse. Explaining the observed characteristics of FRBs, detecting and studying these bursts could be key to uncovering a new layer of cosmic phenomena, deepening our understanding of how magnetic fields behave on extreme scales. Neutron stars are also a source of mystery when it comes to the phenomena known as antimatter. In the extreme environments surrounding neutron stars, high-energy processes can create antimatter particles like positrons. This antimatter can interact with regular matter, producing bursts of gamma rays. Some theories even suggest that regions around neutron stars might contain pockets of antimatter, offering a unique opportunity to study how antimatter behaves in a natural setting. Understanding these interactions is not only fascinating in the context of neutron stars, but could also have implications for understanding the early universe, where antimatter and matter were thought to exist in almost equal amounts. The interaction of neutron stars with dark matter, one of the most elusive substances in the universe, is also a subject of intense research. Dark matter doesn't interact with normal matter in the usual ways, but it does interact through gravity, and neutron stars are among the densest gravitational sources in the universe. Some theories suggest that dark matter particles might accumulate inside neutron stars, potentially affecting their structure or behavior. If enough dark matter collects within a neutron star, it could theoretically ignite unusual processes, possibly even causing the star to collapse into a black hole. By observing neutron stars, scientists hope to detect subtle changes that might indicate the presence of dark matter, opening a new frontier in the quest to understand this mysterious substance. Neutron stars also hold potential clues about the nature of time dilation, a concept derived from Einstein's theory of relativity. Due to their extreme gravitational fields, neutron stars significantly warp space-time, creating a phenomenon where time passes more slowly close to the star than it does far away. This effect is called gravitational time dilation, and it's so pronounced around neutron stars that it can be measured directly. Observing pulsars in binary systems, where two neutron stars orbit each other, allows astronomers to study these time distortions in real time. These observations not only confirm aspects of relativity, but also reveal details about the interplay between gravity and time, providing insights into one of the most fundamental aspects of the universe. In certain conditions, neutron stars might also produce unique forms of radiation known as paraplasma. When particles are accelerated to nearly the speed of light around neutron stars, they can collide and convert into pairs of matter and antimatter particles. This creates a highly energetic plasma that emits radiation across the electromagnetic spectrum. Understanding paraplasma could offer insights into some of the most energetic processes in the universe, and may even have implications for understanding particle physics on Earth. The spin-down of neutron stars, or the gradual slowing of their rotation over time, is another fascinating process. This deceleration is mainly due to the emission of radiation and the interaction of their magnetic fields with surrounding space. As neutron stars lose rotational energy, they emit particles and electromagnetic waves, gradually reducing their speed. Over millions of years, they can slow down to a point where they no longer emit regular pulses, effectively becoming invisible. This process, however, varies depending on the strength of the neutron star's magnetic field and initial rotation speed. By studying this spin-down process, scientists can learn more about the life cycles of neutron stars and the physics of angular momentum. The potential use of neutron stars as gravitational wave sources is another area that has transformed astrophysics. When two neutron stars spiral into each other, they create powerful gravitational waves that ripple through space-time, eventually merging into a single, highly dense object. These waves carry information about the star's masses, composition, and even the behavior of space-time under extreme conditions. Gravitational wave detectors on Earth, such as LIGO and Virgo, have already detected waves from neutron star collisions, marking a new way to observe the universe and revealing insights that would otherwise remain hidden. There's also the idea of neutron star mountains, tiny deformations on the surface of a neutron star caused by its rotation and magnetic field. Though only a few millimeters high, these mountains are significant because they could produce continuous gravitational waves as the star rotates. Detecting these waves would provide a new method for studying neutron stars and might offer clues about their interior structure, magnetic fields, and overall stability. One of the wildest concepts involving neutron stars is the idea of strange matter, a hypothetical state where the neutrons break down even further into particles called strange quarks. Strange matter, if it exists, would be denser and more stable than ordinary neutron star matter. Some scientists suggest that strange matter could even infect other normal matter upon contact, converting it into strange matter as well. This raises the possibility that strange matter could exist in the cores of certain neutron stars, potentially transforming them into strange stars. Discovering such a state of matter would revolutionize our understanding of particle physics and could reveal a new fundamental state of matter. Finally, neutron stars serve as cosmic laboratories for testing theories of quantum mechanics and relativity in ways that are impossible on Earth. The extreme conditions within neutron stars force matter to behave in ways that challenge our current understanding of physics. From the behavior of superfluids in their core to the effects of intense magnetic fields on atomic structures, neutron stars push the boundaries of known science. Each observation, whether it's a glitch in their rotation or a burst of X-rays, helps piece together the puzzle of the universe's most enigmatic objects. In a universe filled with the unexpected, neutron stars remind us of nature's most profound extremes. Every new discovery about them draws us deeper into a cosmic journey that challenges what we know and invites us to look further into the mysteries of space, matter, and the fundamental forces that shape everything around us. As we continue to explore neutron stars, another intriguing concept emerges: their potential role as gravitational laboratories for testing and exploring the edges of Einstein's theory of general relativity. Neutron stars are among the most massive objects that are not black holes, allowing scientists to study gravity in environments far more extreme than anything we experience on Earth. When neutron stars are found in binary systems, where they orbit another neutron star or even a black hole, the gravitational interactions are incredibly complex and intense. These binaries provide a unique setting for observing the effects of gravity, particularly when studying the subtle dance between the two massive objects as they spiral closer and closer together. This spiral can generate gravitational waves that carry vital information about the star's structure, composition, and even the way gravity behaves under these extraordinary conditions, giving us an unprecedented way to test the limits of relativity. Another astonishing phenomenon connected to neutron stars is the creation of ultra-high-energy cosmic rays. These cosmic rays are particles traveling through space at nearly the speed of light, carrying enormous amounts of energy. Scientists have long wondered about the origins of the most energetic cosmic rays detected on Earth, and neutron stars, particularly pulsars, are thought to be a likely source. The intense magnetic fields and rapid rotation of pulsars accelerate particles to extraordinary speeds, launching them into space as cosmic rays. These particles may travel vast distances, eventually reaching our solar system and penetrating Earth's atmosphere, where they can be detected by specialized observatories. Understanding cosmic rays from neutron stars could help us learn about particle acceleration and high-energy processes occurring in other parts of the universe, bringing insights into astrophysical phenomena that extend far beyond neutron stars themselves. Additionally, neutron stars might harbor incredibly exotic states of matter, such as superfluidity within their cores. A superfluid is a phase of matter where particles move without any resistance, flowing as a perfectly frictionless liquid. Inside neutron stars, scientists believe that the extreme density and pressure force neutrons into a superfluid state, allowing them to move freely without energy loss. This superfluid core could help explain some of the unique behaviors observed in neutron stars, like sudden jumps in their rotation rate. The study of superfluids in neutron stars not only illuminates the strange behaviors within these stars, but also contributes to our understanding of quantum mechanics, where superfluidity is a prominent phenomenon. Neutron stars serve as natural laboratories for this, revealing a cosmic version of a quantum phenomenon rarely seen on such a large scale. Neutron stars are also linked to a mysterious phenomenon known as neutrino emissions. Neutrinos are subatomic particles with almost no mass, and they barely interact with matter, making them incredibly difficult to detect. During the birth of a neutron star in a supernova explosion, vast quantities of neutrinos are released, carrying away energy and helping the star stabilize after its violent formation. In some cases, neutron stars can continue emitting neutrinos as they cool, providing a faint but detectable signal. Observing neutrino emissions from neutron stars can offer a unique window into the processes happening in their interior, as neutrinos can escape the dense core without interacting much with surrounding matter. This allows scientists to study the internal dynamics of neutron stars in ways that would otherwise be impossible. The existence of neutron stars also poses questions about island universes within galaxies. These stars are typically formed in supernova explosions that occur within dense stellar environments, often leaving neutron stars isolated in otherwise empty regions of space. However, some neutron stars may get ejected from their birthplace by the immense force of the supernova explosion, propelling them across their galaxies at incredible speeds. These runaway neutron stars move through space alone, sometimes reaching velocities of several hundred kilometers per second. The discovery of these high-velocity neutron stars opens questions about their interactions with galactic material, their paths through space, and their potential encounters with interstellar matter. One particularly exciting area of neutron star research is their potential as probes into the equation of state of dense matter, which is the relationship between pressure, temperature, and density in ultradense conditions. The composition and behavior of matter at the density found inside neutron stars are still largely unknown because it cannot be replicated on Earth. Different models predict different structures and behaviors inside neutron stars, leading to varying theories about their cores. By measuring the mass and radius of neutron stars, astronomers can narrow down which equations of state are possible, allowing them to better understand what lies within these stars. This research could also lead to insights into the behavior of matter during the early moments of the universe, when similar conditions might have existed. In recent years, some scientists have even suggested that neutron stars could be used as cosmic lighthouses for interstellar navigation. Their precise pulses, especially those from millisecond pulsars, provide highly accurate timing signals that could serve as a universal GPS for space travel. If spacecraft were equipped to receive and measure these pulses, they could theoretically navigate by triangulating their position relative to known pulsars. This idea has inspired research into pulsar-based navigation systems, which could be crucial for future missions into deep space where traditional navigation methods become less effective. Using neutron stars in this way could eventually lead humanity to explore distant corners of the galaxy with a degree of precision unimaginable today. Neutron stars also prompt us to consider the potential for new, undiscovered physics. For example, some theorists propose that neutron stars may contain particles or interactions that we haven't yet identified. One idea is that dark matter particles could interact with neutron stars, accumulating in their cores and altering their structure over time. If dark matter does indeed interact with normal matter under extreme conditions, neutron stars could become a testing ground for these interactions. Observing any unusual changes in neutron stars might provide hints about dark matter and its role in the cosmos, paving the way for a deeper understanding of one of the universe's greatest mysteries. Lastly, neutron stars ignite curiosity about their potential for star collapse events. If a neutron star gains enough mass, it can overcome the degeneracy pressure that supports it, collapsing into a black hole. Observing this process directly could reveal a real-time transformation of a star from one state into another, offering a rare glimpse into the conditions necessary to form black holes. This collapse process not only deepens our understanding of stellar evolution, but also sheds light on the final stages of matter in the universe, moving from one extreme, a neutron star, to another, a black hole. Each neutron star observation brings with it new questions, theories, and sometimes completely unexpected phenomena. They are gateways to extreme physics, revealing the nature of matter, energy, and forces in ways that continually challenge our understanding of reality. The mysteries they present act as a reminder that even in an age of immense technological progress, the universe holds secrets that are as baffling as they are beautiful, inviting us to look ever deeper into the cosmos. Continuing our exploration of neutron stars, we come to the phenomenon of X-ray pulsars, which are neutron stars and binary systems that emit X-rays as they interact with a companion star. When a neutron star's intense gravity pulls gas and dust from a nearby star, this material forms an accretion disk around the neutron star, spiraling closer and closer until it heats up to millions of degrees. At such extreme temperatures, the material emits powerful X-rays that we can detect from Earth. These X-ray pulsars give scientists a unique opportunity to study the process of accretion, which plays a crucial role in many cosmic phenomena, including the growth of black holes. By observing the timing and intensity of these X-rays, researchers can learn about the dynamics of mass transfer, the gravitational effects near neutron stars, and the behavior of matter under intense heat and pressure. The study of neutron stars has also introduced the concept of millisecond pulsars, which are neutron stars spinning incredibly quickly, sometimes rotating hundreds or even 1,000 times per second. These rapid spins are typically achieved when a neutron star pulls material from a companion star, a process that transfers angular momentum and increases its rotation speed. Millisecond pulsars are especially valuable for scientists because their precise and stable spin rates make them excellent tools for studying gravitational waves, mapping space-time, and even searching for planets around distant stars. In some cases, astronomers have discovered planets orbiting millisecond pulsars, a phenomenon that raises questions about how these planets could survive or form in such extreme environments. These pulsar planets defy conventional understanding of planetary systems and hint at the diversity of ways in which planets might exist across the cosmos. Another fascinating concept linked to neutron stars is the potential for exotic particle physics within their cores. At the heart of a neutron star, where pressures and densities are at their absolute maximum, ordinary matter may break down into its fundamental components. One possibility is that the neutrons themselves dissolve into quarks, the basic building blocks of protons and neutrons. This state of matter, known as quark matter, would represent an entirely new phase of matter, and it could exhibit behaviors we can only theorize about. If confirmed, the existence of quark matter in neutron stars would redefine our understanding of particle physics and provide insights into how matter behaved in the earliest moments after the Big Bang. Neutron stars are also intriguing when we consider their ability to influence surrounding space through pulsar winds. These winds are streams of highly energetic particles that are emitted from the surface of a rapidly spinning neutron star. As the pulsar spins, its powerful magnetic field accelerates particles to nearly the speed of light, creating an energetic wind that spreads out across space. Pulsar winds can shape the interstellar medium around the neutron star, creating a pulsar wind nebula, a glowing cloud of particles and radiation that surrounds the pulsar. One of the most famous examples of this is the Crab Nebula, which is powered by a pulsar at its center. Studying these nebulae helps scientists understand the interactions between neutron stars and the material around them, revealing the influence of these stars on their surroundings and the life cycle of matter in the galaxy. The immense gravitational field of neutron stars also opens the door to the study of tidal forces in an extreme context. Tidal forces occur when gravitational forces from one object stretch another, and these effects are especially pronounced when a neutron star interacts with a companion star or another neutron star. In binary systems, the tidal forces from a neutron star can distort and even pull apart a companion star, drawing its material into an accretion disk. During neutron-star mergers, tidal forces become so intense that they can warp and disrupt both stars, producing gravitational waves that ripple across space-time. By observing these interactions, scientists gain insights into the physics of gravity and tidal dynamics under the most extreme conditions possible. In recent years, researchers have also speculated about the existence of gravitational wave echoes that could be produced when neutron stars collide. These echoes, if detected, would be subtle ripples following the main gravitational wave signal from the collision, hinting at complex interactions between the neutron star material and gravity itself. Detecting these echoes could offer an entirely new way to study the interior composition of neutron stars, revealing the behavior of ultradense matter and possibly even supporting theories that go beyond Einstein's theory of relativity. The possibility of neutron stars forming boson clouds around themselves is yet another area of theoretical intrigue. Some physicists hypothesize that dark matter may be composed of exotic particles known as bosons, which could form dense clouds around neutron stars if they exist in the right conditions. These boson clouds would interact weakly with a neutron star, potentially altering its gravitational signature and rotational behavior in subtle ways. If such clouds were detected, it would provide strong evidence for certain types of dark matter, opening a groundbreaking avenue in the search for this elusive component of the universe. This interaction between dark matter and neutron stars remains largely theoretical, but it is a topic of active research, as it could lead to one of the most significant discoveries in modern astrophysics. The exploration of neutron stars has even inspired ideas about quantum gravity, a theoretical framework that attempts to unify quantum mechanics with general relativity. Neutron stars represent a unique convergence of these two realms, as their structure is influenced by both the quantum forces acting on particles within their core and the powerful gravitational field surrounding them. Studying neutron stars could provide clues about the nature of quantum gravity, especially as scientists observe phenomena that seem to bridge the gap between quantum and relativistic effects. Understanding quantum gravity would represent a major leap in physics, potentially solving one of the greatest challenges in the field by connecting the physics of the very small with the physics of the very large. A particularly speculative but intriguing idea involves the possibility of neutron stars acting as wormhole gateways. While purely theoretical, some researchers have speculated that the extreme conditions within neutron stars could theoretically create or stabilize wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe. Although there is no evidence that wormholes actually exist, the unique environment within neutron stars makes them a potential candidate for such exotic structures, according to certain theories of space-time. If such phenomena were ever observed, it would revolutionize our understanding of the cosmos and provide a pathway toward faster-than-light travel, one of the most sought-after ideas in theoretical physics. Neutron stars are also considered in studies of cosmic evolution, as they represent a crucial phase in the life cycle of massive stars. When massive stars explode as supernovae, they leave behind neutron stars as a transitional state, which may eventually evolve into black holes. These stars illustrate the transformative processes of stellar evolution and contribute to the enrichment of galaxies with heavy elements. By studying neutron stars and their distribution across galaxies, scientists can better understand the history of stellar populations, the formation of elements, and the ways in which galaxies evolve over billions of years. Finally, neutron stars are fundamental to our understanding of the life cycle of matter in the universe. From the explosive birth of neutron stars and supernovae to their potential collisions that spread heavy elements across space, these stars play an essential role in recycling matter. The elements produced in and around neutron stars, like gold, platinum, and uranium, are scattered throughout space, eventually becoming part of future stars, planets, and even life. Neutron stars serve as cosmic engines that both destroy and create, contributing to the perpetual cycle that drives the evolution of matter across the cosmos. Each discovery about neutron stars propels us further into the unknown, challenging our understanding of the universe at every level. Their existence pushes the limits of physics, inviting us to delve deeper into mysteries that defy conventional knowledge. As research continues, neutron stars remain one of the most fascinating subjects in astrophysics, revealing new wonders with every observation and reminding us that the cosmos holds far more than we could ever imagine. Another intriguing aspect of neutron stars is the concept of gravitational redshift, which occurs because of the intense gravity these stars exert on their surroundings. When light or radiation escapes from a neutron star, it loses energy due to the gravitational pull, stretching the light waves and causing them to shift to longer, redder wavelengths. This effect, known as gravitational redshift, is so extreme around neutron stars that the light can be shifted far beyond what we would normally observe in less intense environments. By measuring the redshift in radiation emitted from neutron stars, scientists gain direct evidence of the gravitational strength near these dense objects, providing a test for general relativity under some of the most extreme conditions imaginable. Neutron stars also push the limits of our understanding through their role in gamma-ray bursts, GRBs, some of the most powerful explosions observed in the universe. When two neutron stars collide, they release a colossal amount of energy, producing a short but intensely bright burst of gamma rays. These short gamma-ray bursts are thought to mark the violent merger of two neutron stars, or, in some cases, a neutron star merging with a black hole. These bursts release more energy in a matter of seconds than our Sun will emit over its entire 10 billion-year lifespan. Observing GRBs allows scientists to explore extreme physics, shedding light on neutron star mergers and the role of these events in the cosmic distribution of heavy elements like gold and platinum. The intense magnetic fields of neutron stars also create unique environments for studying quantum electrodynamics, QED, which describes how light and matter interact at the smallest scales. In regions near a neutron star, the magnetic field can be so strong that it actually influences the vacuum of space, altering the behavior of photons as they pass through. This effect, known as vacuum birefringence, was predicted by QED but is nearly impossible to observe directly on Earth. However, the extreme magnetic fields near neutron stars provide a natural laboratory for observing these quantum effects. Detecting and studying vacuum birefringence in neutron star environments would not only confirm predictions of QED, but also enhance our understanding of how light behaves under some of the universe's most extreme conditions. Neutron stars may also give rise to exotic forms of matter such as hyperons or kaons, particles that are usually too unstable to exist under normal conditions. Inside a neutron star, however, the extreme pressure might allow these particles to exist in a stable form, introducing a new phase of matter. Hyperons, for example, are particles that contain strange quarks, a type of particle typically only seen in high-energy experiments on Earth. If hyperons or other exotic particles are present within neutron stars, they would affect the star's mass, radius, and even its rotational dynamics. By studying the structural properties of neutron stars, astronomers can indirectly probe for these exotic particles, potentially discovering new states of matter that could only exist in the extreme environment of a neutron star's core. The study of neutron stars has also led scientists to consider the concept of superconductivity within these stars. Superconductivity is a state in which electrical resistance drops to zero, allowing currents to flow without any energy loss. Under the extreme pressures and temperatures within a neutron star, particles may form Cooper pairs, enabling a form of superconductivity. This phenomenon, if present, could influence the magnetic field behavior and rotational properties of neutron stars. Understanding superconductivity in neutron stars might have applications beyond astrophysics, as it provides insights into quantum states of matter that could one day be replicated or utilized in advanced materials or technologies. One of the most captivating recent discoveries involves neutron stars that emit bursts of soft gamma rays in a phenomenon known as soft gamma repeaters. These bursts are thought to come from magnetars, a type of neutron star with an exceptionally powerful magnetic field. Occasionally, a magnetar's magnetic field undergoes a sudden reconfiguration, releasing a massive amount of energy as a soft gamma ray burst. These bursts, though short-lived, are highly energetic, capable of affecting the surrounding space. Observing these bursts provides a rare glimpse into the magnetic processes within neutron stars, offering insights into magnetic reconnection and particle acceleration, processes that are difficult to study even on Earth. The interactions of neutron stars with surrounding gas and dust may also lead to the formation of shock waves that move through space, energizing nearby particles. When a neutron star emits a strong magnetic pulse or collides with material around it, shock waves ripple outward, heating the surrounding gas and causing it to emit X-rays or even gamma rays. These shock waves, in turn, can influence the evolution of nearby stellar material, creating regions of ionized gas and forming structures that are visible across the electromagnetic spectrum. Studying these shock waves helps scientists understand the complex interplay between neutron stars and their environment, revealing how these stars affect the interstellar medium around them. Another area of fascination with neutron stars involves the potential presence of photon spheres, regions where gravity is so intense that light can orbit the star. This effect is typically associated with black holes, but neutron stars, with their extreme gravitational fields, may have regions near their surface where light is bent into a circular path. In theory, a photon sphere around a neutron star would allow light to orbit the star multiple times before escaping, creating unusual visual effects and potentially making the star appear as if it were surrounded by rings or arcs of light. Observing these effects would provide a rare look at how light behaves under intense gravity, offering a glimpse into relativistic optics in the strong field regime. Neutron stars also invite speculation about the possibility of axion stars. Axions are hypothetical particles that are a candidate for dark matter, and under certain conditions, axions could form clumps or stars near neutron stars. If axions exist, they could interact with the magnetic fields around neutron stars, potentially producing detectable signals in the radio or gamma ray spectrum. Detecting axions around neutron stars would be groundbreaking, offering not only potential evidence for dark matter, but also a new way to study its interactions with ordinary matter under unique conditions. The concept of frame dragging also emerges in the study of neutron stars, particularly in binary systems. Frame dragging is an effect predicted by general relativity, where the rotation of a massive object like a neutron star twists the surrounding space-time, pulling it along with the star's rotation. In binary systems, where two neutron stars orbit each other closely, frame dragging effects can become pronounced, influencing the orbital dynamics and even affecting the star's rotation rates. Observing frame dragging near neutron stars provides one of the few ways to study this relativistic effect outside of black hole environments, allowing scientists to refine their models of how gravity and rotation interact in extreme astrophysical objects. Neutron stars are also significant in our understanding of cosmic recycling. When neutron stars merge or undergo extreme outbursts, they spread elements and energy into surrounding space, contributing to the cycle of matter in galaxies. This distribution of elements, especially heavy ones created in neutron star collisions, enriches the interstellar medium, providing the building blocks for new stars and planets. Over cosmic timescales, Neutron stars play a pivotal role in seeding galaxies with the raw materials needed for future generations of stars and planetary systems, including elements essential to life itself. The study of neutron stars continues to reveal astonishing facts about the universe and challenges our fundamental understanding of matter, gravity, and quantum physics. Each discovery about these stellar remnants hints at deeper mysteries waiting to be unraveled. In their intense gravity, extreme magnetic fields, and unique interactions with surrounding matter, neutron stars offer a glimpse into the universe's most powerful and enigmatic forces. As astronomers and physicists probe deeper, neutron stars remind us that the cosmos is filled with phenomena that push the boundaries of knowledge, inviting us to explore the extraordinary realities that lie beyond our current understanding. Delving deeper into the mysteries of neutron stars, we encounter the enigmatic idea of neutron drip. This phenomenon occurs in the outer layers of neutron stars, where the gravitational force is so intense that it pushes atomic nuclei to their breaking point. Under these extreme conditions, electrons are forced into protons, creating neutrons that drip out of the nucleus and join a superdense neutron-rich fluid. This neutron drip layer is thought to play a key role in the structure of the neutron star, influencing its crust and helping to create the unique, layered structure that defines these stars. Studying neutron drip allows scientists to explore nuclear physics on an unprecedented scale, revealing how atomic particles behave under the universe's most extreme pressures. One of the most exciting hypotheses about neutron stars is their potential to host Q-ball dark matter. Q-balls are hypothetical particles predicted by certain theories of supersymmetry, which is a proposed extension of the standard model of particle physics. In the intense gravitational fields of neutron stars, it's speculated that Q-balls might cluster and interact with the neutron star's material. If they exist, Q-balls could affect the neutron star's rotation or temperature, creating subtle effects that might eventually be detectable. Studying Q-ball interactions with neutron stars could provide evidence of supersymmetry and shed light on the nature of dark matter, offering a potential breakthrough in our understanding of the universe's hidden components. The phenomenon of glitches in neutron stars provides yet another layer of intrigue. Glitches are sudden changes in the rotational speed of a neutron star, believed to result from interactions between its crust and superfluid core. In a typical glitch, the superfluid core transfers angular momentum to the crust, causing a momentary speed up. This process reveals the unique internal dynamics of neutron stars, where the outer crust and inner core behave almost like separate entities. Observing and studying these glitches provides clues about the material properties within neutron stars, offering a rare glimpse into how superfluid and solid matter interact under immense pressure. Each glitch helps refine our models of neutron star interiors, giving scientists clues about their superfluid nature and the forces at play in such extreme environments. Neutron stars are also linked to cosmic strings, hypothetical one-dimensional defects in space-time predicted by some theories of the early universe. If cosmic strings exist, they could occasionally pass through neutron stars, creating bursts of gravitational waves and potentially influencing the star's rotation or magnetic field. The immense density of neutron stars would make them sensitive to the presence of such strings, providing a rare opportunity to detect these elusive objects. If cosmic strings were detected around neutron stars, it would offer a glimpse into the fabric of space-time itself, opening a window into the conditions that existed shortly after the Big Bang and potentially revealing new dimensions of reality. In the realm of particle physics, neutron stars might also provide clues about sterile neutrinos, a hypothetical form of neutrino that interacts only through gravity. Neutrinos are usually difficult to detect because they barely interact with other matter, but sterile neutrinos would be even more elusive. However, if they exist, sterile neutrinos could influence the cooling process of neutron stars, changing how quickly these stars lose heat over time. By analyzing the thermal evolution of neutron stars, scientists hope to detect signs of sterile neutrinos, which would have profound implications for particle physics and cosmology, potentially offering insights into the mass and behavior of dark matter. Neutron stars also hold potential clues about the island of stability in nuclear physics. The island of stability refers to a theoretical region in the periodic table where superheavy elements with unusually stable atomic nuclei might exist. While elements heavier than uranium, tend to decay rapidly. Certain configurations of protons and neutrons could theoretically create long-lived superheavy elements. The conditions inside neutron stars might allow these elements to form and remain stable, creating a type of matter that we cannot replicate on Earth. If such elements exist within neutron stars, they could provide insights into the structure of atomic nuclei and reveal unknown aspects of nuclear stability. Another aspect of neutron stars that fascinates scientists is the idea of spin equilibrium. Neutron stars are born spinning rapidly, but over time, their spin rate can change due to magnetic braking, gravitational interactions, and accretion of material from companion stars. In binary systems, neutron stars can reach a balance, or equilibrium, where their spin rate stabilizes due to the competing forces at play. This equilibrium state provides valuable information about the forces acting on the neutron star, helping scientists understand the complex balance between angular momentum, magnetic fields, and gravitational interactions. Observing neutron stars in spin equilibrium allows researchers to refine their models of stellar evolution and the behavior of matter under intense gravitational forces. In terms of thermodynamics, neutron stars present an extreme case of adiabatic processes, where changes in the star's temperature or pressure can occur without any heat exchange with the surroundings. Because neutron stars are isolated in the vacuum of space, changes within them often occur adiabatically, meaning that their internal processes unfold under conditions of extreme temperature and pressure without any cooling or heating from external sources. This unique setting allows astrophysicists to study adiabatic processes on an unimaginable scale, providing insights into thermodynamic principles that govern not only neutron stars, but also the behavior of matter in high-energy environments. Neutron stars may also hold the key to understanding fermionic condensates, a state of matter formed by fermions, particles like protons and neutrons, at ultra-low temperatures. Within the superfluid core of a neutron star, fermionic condensates might form, resulting in a state where particles move in perfect synchrony. This behavior is rare and difficult to achieve on Earth, but neutron stars could naturally host fermionic condensates in their cores. Studying this condensate state would provide valuable information on quantum mechanics and the behavior of fermions in extreme conditions, potentially leading to advances in material science and quantum computing. The concept of neutron stars emitting giant flares is another area of interest, especially when it comes to magnetars. Magnetars, with their immense magnetic fields, can undergo sudden magnetic reconnections, releasing energy in the form of giant flares. These flares are thousands of times more powerful than typical solar flares and can release energy equivalent to millions of times the Earth's annual energy consumption in just a few seconds. Such flares are capable of disrupting satellite communications and even affecting Earth's ionosphere if they occur within a certain distance. Observing these giant flares gives scientists insight into magnetic energy release and particle acceleration under extreme conditions, offering valuable data for understanding similar processes on a smaller scale within our own sun. Another intriguing theoretical concept involves neutron stars as strange attractors in dynamical systems. In physics, strange attractors are patterns that emerge in chaotic systems, and neutron stars, with their complex rotational and magnetic behaviors, may display strange attractor dynamics. If such patterns are present, they could reveal underlying rules governing the seemingly chaotic magnetic fields and rotation rates of neutron stars. Detecting strange attractor behaviors in neutron stars would enhance our understanding of chaotic systems and help scientists develop more accurate models of stellar magnetism and rotational dynamics. The notion of quantum tunneling within neutron stars is also worth exploring. Quantum tunneling is a phenomenon where particles pass through barriers that would normally be impenetrable in classical physics. In the intense pressures inside neutron stars, particles might quantum tunnel through the dense nuclear matter, contributing to processes like neutron decay or even affecting the star's temperature and structure. Studying quantum tunneling in neutron stars would provide a natural laboratory for observing this quantum phenomenon on a massive scale, deepening our understanding of particle interactions and quantum mechanics. Lastly, neutron stars embody the idea of gravitational collapse, a process that continues to transform our understanding of stellar evolution. A neutron star represents a balance between collapse and the forces supporting it. But if it gains enough mass, it can no longer resist its own gravity and collapses into a black hole. This final transformation marks one of the most dramatic events in the universe, where a star reaches the ultimate state of density and compaction. Observing neutron stars that are on the brink of collapse could provide real-time insights into this process, giving scientists an opportunity to witness the threshold where neutron stars become black holes, offering answers to fundamental questions about gravity, matter, and the limits of star formation. In every aspect, neutron stars represent nature's extremes, pushing the boundaries of density, magnetism, quantum mechanics, and thermodynamics. Each discovery in the realm of neutron stars reveals new dimensions of our universe, inviting us to contemplate not only the stars themselves, but the very nature of reality. The study of neutron stars is a journey into the unknown, where each observation challenges the limits of science and unveils the secrets of the cosmos, reminding us that the universe holds wonders beyond our wildest imagination. Building upon the mysteries of neutron stars, we encounter the extraordinary concept of tidal disruption events, TDEs, involving neutron stars and binary systems with black holes. When a neutron star orbits a black hole closely, the black hole's immense gravity can pull apart the neutron star, stretching it into a stream of matter. This process, known as spaghettification, results in a tidal disruption event, releasing a tremendous amount of energy as the neutron star is torn apart. These events produce brilliant flares of radiation, detectable from millions of light years away, and provide scientists with a unique window into how black holes interact with other dense stellar objects. By studying TDEs involving neutron stars, researchers gain valuable insights into the boundaries between neutron stars and black holes, shedding light on the final moments of these enigmatic stars and the intense gravitational forces in their vicinity. In addition to these violent interactions, neutron stars are also studied for their potential role in asymmetric dark matter theories. Some dark matter models propose that dark matter particles have slightly different properties than normal matter, potentially leading to an imbalance that could be detectable under extreme conditions. Neutron stars, with their intense gravitational fields and dense interiors, might act as natural traps for these asymmetric dark matter particles. If such particles are captured by neutron stars, they could gradually accumulate in the star's core, eventually affecting its structure and behavior. Detecting changes in neutron stars that could indicate dark matter presence would represent a groundbreaking step toward understanding one of the most elusive components of the universe, offering hints about dark matter's nature and its role in shaping cosmic structures. One fascinating aspect of neutron stars is their ability to host R-mode oscillations, a type of fluid oscillation that occurs when a star's rotation interacts with its internal gravitational field. These oscillations are thought to be driven by the emission of gravitational waves, causing the neutron star to emit periodic ripples in spacetime. R-mode oscillations can cause the star to lose rotational energy, slowing it down over time. By observing neutron stars with these oscillations, scientists can directly study the emission of gravitational waves and understand the internal dynamics that create these oscillations. This research provides a unique opportunity to test predictions about gravitational wave emissions and contributes to our understanding of stellar rotation and stability in extreme environments. The potential existence of nuclear pasta within the crust of neutron stars adds yet another layer of intrigue. Nuclear pasta refers to unique structures formed by protons and neutrons under extreme pressures, creating shapes like sheets, tubes, and clumps that resemble different types of pasta. These structures are thought to be incredibly strong, perhaps even the strongest material in the universe. Nuclear pasta plays a significant role in a neutron star's crust, affecting how it responds to stress and potentially contributing to starquakes and other surface phenomena. Studying nuclear pasta offers insights into the behaviors of nuclear matter under conditions that cannot be replicated on Earth, providing a glimpse into the strength and flexibility of matter at a subatomic level. The idea of neutron stars as cosmic magnetospheres also captures the imagination of scientists. A neutron star's powerful magnetic field creates an extensive magnetosphere that interacts with particles in the surrounding space. This magnetosphere accelerates particles to high energies, creating beams of radiation and potentially even causing phenomena like auroras on nearby companion stars. In certain cases, neutron stars and binary systems can produce magnetic interactions that are detectable as X-ray and gamma-ray flares. Studying these magnetospheres helps scientists understand not only neutron stars, but also magnetic fields across the universe, shedding light on how magnetism influences astrophysical processes on both small and large scales. In a remarkable twist, neutron stars might even serve as standard candles in cosmology. Traditionally, standard candles like supernovae are used to measure distances across the universe because their luminosity is predictable. Neutron stars, particularly pulsars, with their precise rotational periods and predictable radiation patterns, could potentially be used in a similar way. By observing the timing and frequency of pulsar emissions across different galaxies, scientists could refine distance measurements on a cosmic scale. If neutron stars can be reliably used as standard candles, they would become powerful tools for mapping the structure of the universe, helping us understand the expansion of space and the distribution of galaxies across vast cosmic distances. Neutron stars are also valuable for studying high-density quark-gluon plasmas. In their cores, under pressures and densities far beyond what we can replicate on Earth, quarks, the fundamental components of protons and neutrons, may exist in a plasma state, freed from their usual bonds. This quark-gluon plasma is believed to be similar to the state of matter that existed just moments after the Big Bang. Observing neutron stars provides indirect evidence for this plasma and gives physicists a way to study the behaviors of quarks in extreme conditions. Understanding quark-gluon plasmas could reveal the processes that governed the early universe, helping scientists trace the history of matter from the Big Bang to the formation of stars and galaxies. One intriguing hypothesis proposes that some neutron stars might host superfluid vortex arrays in their cores. As neutron stars rotate, the superfluid within their cores forms vortex lines, much like tiny tornadoes that align with the star's rotational axis. These vortex arrays play a crucial role in maintaining the star's rotation and could be connected to the glitches observed in pulsars. When the alignment of these vortices shifts, it can lead to sudden changes in the star's rotation speed. By studying these vortices, scientists can explore the properties of superfluids on a cosmic scale and gain insights into how rotation and angular momentum are maintained in dense, compact objects. Neutron stars are also associated with the concept of phase transitions within their cores. At certain densities and pressures, matter might undergo phase transitions, similar to how water turns into ice or steam at specific temperatures and pressures. Inside neutron stars, phase transitions could occur as neutrons break down into quarks, potentially leading to the formation of exotic phases of matter, like quark matter or color superconductors. Observing these phase transitions could reveal the behavior of matter under conditions that are otherwise unachievable, pushing the boundaries of nuclear physics and enhancing our understanding of the fundamental forces that govern matter. The study of neutron stars also raises questions about holographic principles in physics. Some theories propose that the universe might be described as a hologram, where all the information contained within a volume of space is encoded on its boundary. Neutron stars, with their extreme gravity and compact structure, could serve as a natural testing ground for holographic principles. If these principles hold true in neutron star environments, it could indicate that information about the star's internal structure is somehow encoded on its surface. This concept, though speculative, offers an entirely new way of thinking about space, matter, and information in the cosmos, potentially revealing new dimensions to the universe's structure. Another area of study focuses on resonant frequency modes within neutron stars. Much like musical instruments that vibrate at specific frequencies, neutron stars can oscillate at particular resonant frequencies, depending on their internal structure and composition. These oscillations, or starquakes, produce gravitational waves that carry information about the star's inner layers. Observing these resonant frequencies allows scientists to conduct stellar seismology, using the vibrations to map the star's interior, much like how seismic waves are used to study the Earth's interior. Stellar seismology of neutron stars could provide clues about their core composition, density gradients, and even the existence of exotic states of matter. Neutron stars also bring up the possibility of quantum chromodynamics, QCD, in action. QCD is the theory that describes how quarks and gluons interact to form protons, neutrons, and other particles. The extreme conditions inside neutron stars create an environment where QCD can be tested in ways that are impossible in Earth-based labs. By studying neutron stars, scientists hope to uncover the ways in which quarks and gluons behave under extreme pressure, helping to bridge the gap between theoretical models and observable reality. This research might lead to new insights into the strong nuclear force, one of the fundamental forces in nature, which governs the structure of atomic nuclei. Lastly, neutron stars represent a gateway into the multi-messenger approach to astronomy, where scientists use multiple forms of cosmic information, such as gravitational waves, electromagnetic radiation, and neutrinos, to study a single event. Neutron star mergers, for example, emit both gravitational waves and electromagnetic signals, allowing researchers to analyze these events from multiple angles. This multi-messenger approach has revolutionized our understanding of neutron stars and the cosmos, offering a comprehensive view of the physics involved in these extreme environments. By combining observations from various messengers, scientists gain a deeper, multidimensional view of the universe, uncovering insights that would be inaccessible through any single form of observation. Neutron stars remain one of the universe's most enigmatic and powerful objects, pushing the boundaries of what we know about physics, astronomy, and the nature of matter. Each discovery about these stellar remnants opens new paths of inquiry, inviting us to confront questions that challenge the very foundation of our understanding. As we continue to observe and explore neutron stars, we are reminded of the universe's complexity and the endless layers of mystery that lie within, each revealing a deeper truth about the cosmos and our place within it. Moving forward in our journey through the mysteries of neutron stars, we encounter the concept of thermonuclear bursts that occur on their surfaces, particularly in binary systems where a neutron star accretes matter from a companion star. As this material builds up on the neutron star surface, it eventually reaches a critical density and temperature, triggering a rapid, runaway, thermonuclear explosion. This burst releases an immense amount of energy in just a few seconds, producing X-rays that can be detected from Earth. These explosions, known as Type 1 X-ray bursts, are some of the most energetic events in the universe and allow scientists to study nuclear reactions and fusion processes in conditions far beyond what can be achieved in terrestrial laboratories. By observing these bursts, astronomers gain insights into the properties of neutron stars' outer layers, the behavior of nuclear matter under intense pressures, and the dynamics of accretion in binary systems. Another fascinating area of study involves the potential of neutron stars to host exotic compact objects, ECOs. ECOs are theoretical constructs that lie between neutron stars and black holes, potentially involving unknown states of matter that defy conventional physics. These objects may include hypothetical particles like boson stars, axion stars, or even objects made of dark matter. Neutron stars, with their unique composition and extreme density, could serve as the perfect breeding ground for these exotic forms of matter. If such objects exist within or near neutron stars, they could affect the star's gravitational signature, rotational speed, or magnetic field in subtle but detectable ways. Discovering ECOs would open an entirely new chapter in astrophysics, allowing scientists to explore uncharted territories of matter and uncover potential pathways to new states of existence. Neutron stars are also central to the study of relativistic jets, streams of particles that are accelerated to nearly the speed of light and launched from the star's magnetic poles. These jets are commonly associated with black holes, but certain types of neutron stars, particularly pulsars, are capable of producing similar relativistic jets. The mechanism behind these jets is believed to involve intense magnetic fields and rotational energy, which work together to propel particles outward. Observing relativistic jets from neutron stars helps scientists understand the mechanisms of particle acceleration, magnetic field interactions, and the role of high-energy physics in shaping cosmic structures. These jets also serve as powerful tools for probing the interstellar medium, as they interact with and illuminate the surrounding space. The study of gravitational lensing around neutron stars provides another intriguing avenue of exploration. Due to their high density and strong gravitational fields, Neutron stars can bend light from background objects, creating distorted or magnified images of stars and galaxies positioned behind them. This effect, known as gravitational lensing, allows astronomers to study both the neutron star's mass and the properties of distant cosmic objects. In certain cases, gravitational lensing by neutron stars may even produce Einstein rings, circular patterns of light that reveal the geometry of space-time around these stars. Observing these rings and other lensing effects provides direct tests of Einstein's general relativity, helping scientists refine their understanding of gravity in extreme environments and gain insights into the distribution of mass in distant galaxies. The concept of differential rotation within neutron stars is another area of intense research. Unlike rigid bodies, neutron stars may exhibit differential rotation, meaning that different layers rotate at different speeds. This rotation is influenced by the star's internal structure, magnetic fields, and the presence of a superfluid core. Differential rotation can lead to complex interactions within the neutron star, generating magnetic fields and causing instabilities that affect the star's spin rate and magnetic field configuration. Studying differential rotation allows scientists to probe the inner structure of neutron stars, revealing how matter behaves in highly dense and rotating environments. It also provides insights into the star's magnetic field dynamics and the formation of pulsar beams. The potential of neutron stars to emit radio halos adds yet another layer to their study. While pulsars are known for their focused beams of radio waves, some neutron stars may also emit diffuse halos of radio emissions, extending far beyond the star itself. These radio halos are believed to be produced by interactions between the neutron star's magnetic field and particles in the surrounding space, creating a glowing shell of radio waves around the star. Observing these halos allows scientists to study the interaction between neutron stars and the interstellar medium, shedding light on the star's environment, magnetic field structure, and the broader galactic ecosystem in which it resides. In recent years, researchers have also turned their attention to the possibility of hidden planets orbiting neutron stars. While planets around neutron stars would experience extreme radiation and gravitational forces, it is possible that some planets could form from the remnants of supernova explosions or from material captured by the neutron star. These planets would have highly unusual conditions, with their surfaces bombarded by high-energy radiation and gravitational forces far stronger than on Earth. Discovering planets around neutron stars would offer a new perspective on planetary formation and survival, revealing the resilience of planetary systems in even the most extreme environments. Another remarkable area of study is pulsar timing arrays, which involve using the precise timing of pulsar emissions as a cosmic detector for gravitational waves. By monitoring multiple pulsars across the sky, scientists can detect tiny changes in their timing caused by passing gravitational waves, which subtly stretch and compress space-time. This method allows for the detection of low-frequency gravitational waves, providing a way to observe merging supermassive black holes in distant galaxies or other massive cosmic events. Pulsar timing arrays represent an innovative approach to gravitational wave astronomy, harnessing the precision of neutron star rotations to create a galaxy-wide observatory that can detect events on scales far beyond what Earth-based detectors can achieve. The study of rotating neutron stars in different environments has also led to fascinating discoveries. In regions with high magnetic fields or intense gravitational interactions, neutron stars can exhibit variations in their spin-down rates, rotational speeds, and magnetic field strengths. These variations reveal the complex interplay between a neutron star's rotation and its surrounding environment, helping scientists understand how these stars evolve over time. Observing rotating neutron stars in diverse settings allows researchers to compare the effects of various forces on the star's behavior, creating a comprehensive picture of neutron star dynamics and shedding light on the processes that govern the life cycles of these compact objects. One particularly exciting frontier in neutron star research is the search for dark stars, hypothetical objects composed primarily of dark matter that could exist near neutron stars. If dark matter particles interact with ordinary matter in specific ways, they could form dense clumps around neutron stars, potentially influencing their temperature, rotation, or magnetic field. Detecting signs of dark matter around neutron stars would provide direct evidence of this mysterious substance, offering a breakthrough in our understanding of dark matter's properties and distribution in the universe. By searching for dark stars or dark matter signals around neutron stars, scientists aim to uncover one of the most significant cosmic mysteries of our time. The idea of neutron stars as cosmic clocks further illustrates their unique role in astrophysics. Due to their precise and stable rotation rates, pulsars can serve as natural timekeepers, allowing astronomers to measure time with exceptional accuracy. This property makes neutron stars valuable tools for testing fundamental physics, such as the constancy of physical constants over time or the potential variations in gravitational strength across the universe. Using neutron stars as cosmic clocks allows scientists to test theories of time and space, creating benchmarks for understanding the fundamental nature of reality on cosmic scales. The relationship between neutron stars and fossil magnetic fields is another area of active research. Fossil magnetic fields are believed to be remnants of the magnetic fields present in the progenitor stars before they collapsed into neutron stars. These fields can become intensified during the collapse, leading to the formation of magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. By studying fossil magnetic fields in neutron stars, scientists can trace the magnetic history of stars and gain insights into how magnetic fields evolve across stellar life cycles, providing clues about the role of magnetism in star formation, collapse, and the processes that give rise to different types of neutron stars. Finally, neutron stars are vital to our understanding of element synthesis in the cosmos. When neutron stars merge, they create conditions for the rapid capture of neutrons by atomic nuclei, a process known as the R process. This process produces many of the heavy elements found in the universe, including gold, platinum, and uranium. The material ejected from neutron star mergers spreads across space, seeding new stars, planets, and even life with these elements. Studying element synthesis in neutron star collisions helps scientists understand the origins of the elements we observe today, tracing the cosmic pathways that led to the creation of the building blocks of planets and life. In every way, neutron stars challenge the boundaries of our knowledge and push the limits of physics, offering a laboratory for exploring the fundamental forces and particles that shape the universe. They continue to reveal secrets about the behavior of matter, energy, and space-time under extreme conditions, each discovery opening new doors to the mysteries of existence. The study of neutron stars is a testament to humanity's pursuit of knowledge, reminding us that the cosmos holds wonders beyond imagination, and that each breakthrough brings us one step closer to understanding the profound nature of our universe. Continuing our exploration of neutron stars, we come to the concept of pulsar glitches and anti-glitches, phenomena that reveal the unique interplay between a neutron star's crust and its superfluid core. A glitch is a sudden, slight increase in the pulsar's rotation rate, believed to be caused by interactions between the solid crust and the superfluid layer beneath it. Occasionally, however, the opposite occurs, an anti-glitch, where the pulsar's rotation rate unexpectedly slows down. Anti-glitches are rarer and more difficult to explain, sparking debates about whether they could be linked to magnetic field changes, internal restructuring, or even unobserved interactions between superfluid vortices. Studying these rotational anomalies helps scientists probe the mysterious interior dynamics of neutron stars, offering a glimpse into how superfluidity, solid crusts, and intense magnetic fields interact in ways that defy conventional physics. Neutron stars are also essential to the study of precession, a gradual wobble in the star's rotational axis. This wobble is similar to the motion of a spinning top and occurs due to the complex distribution of mass and magnetic fields within the neutron star. Over time, this precession can alter the orientation of the pulsar's beam relative to Earth, affecting how often and intensely we observe its pulses. By studying the precession of neutron stars, scientists gain insights into the star's internal structure, shape, and magnetic field distribution. In some cases, precession could even indicate the presence of asymmetries in the star's interior, such as uneven distribution of mass or potential mountains on the neutron star's crust, which are tiny irregularities only a few millimeters tall, but incredibly dense. Another area of fascination involves neutron stars with extreme spin-down rates. Over time, neutron stars gradually lose rotational energy due to electromagnetic radiation and particle wind emissions, causing their spin to slow. However, some neutron stars exhibit unusually rapid spin-down rates, suggesting that additional factors are at play. For instance, magnetic interactions with surrounding material or accretion from a companion star can accelerate this slowdown process. Observing these variations in spin-down rates allows scientists to study how neutron stars evolve over time, revealing how external forces and magnetic fields shape their rotational behavior. Understanding spin-down rates is essential for predicting the long-term behavior of neutron stars and provides insights into the aging process of these dense remnants. In recent years, researchers have also focused on the concept of frozen stars, a theoretical state where a neutron star's cooling rate significantly slows, effectively freezing it at a specific temperature. This state could occur if a neutron star's cooling is inhibited by the presence of exotic particles or certain types of matter in its core, such as hypothetical dark matter particles. Frozen stars would cool at a drastically slower rate than typical neutron stars, remaining warm for extended periods. Detecting frozen stars would open up new lines of inquiry into the role of exotic particles in neutron stars, potentially providing evidence of dark matter interactions within these dense environments. Neutron stars may also shed light on the phenomenon of torsional oscillations, vibrations within the star that twist and distort its magnetic field. These oscillations can produce X-ray and gamma-ray flares, especially in magnetars, where the intense magnetic field is prone to sudden reconfigurations. Torsional oscillations occur when magnetic stresses within the crust cause it to twist slightly, transferring energy to the star's magnetic field and emitting bursts of radiation. Studying these oscillations provides insights into the strength and stability of neutron star crusts, the behavior of magnetic fields under extreme pressure, and the mechanisms behind powerful magnetar flares. Another fascinating aspect of neutron stars is the possibility of spacequakes, which are sudden shifts in the crust similar to earthquakes on Earth. Spacequakes are believed to occur when the immense stresses caused by the neutron star's intense gravity and magnetic field build up, eventually causing a rupture in the crust. These quakes release energy in the form of seismic waves, producing X-ray or gamma-ray bursts observable from Earth. By studying these spacequakes, scientists gain insights into the material properties of neutron star crusts, including their strength, elasticity, and ability to withstand immense pressure. Spacequakes also hint at the dynamic nature of neutron star surfaces, showing that even dead stars can exhibit sudden bursts of activity. Neutron stars are also considered in the context of neutrino cooling. Shortly after formation, neutron stars are incredibly hot, with temperatures reaching billions of degrees. As they cool, they emit vast amounts of neutrinos, which carry away energy and gradually lower the star's temperature. Neutrino cooling occurs primarily in the first few 100,000 years of a neutron star's life, and is one of the most effective cooling mechanisms in the universe. By observing neutron stars at different ages and measuring their temperatures, scientists can study the role of neutrino cooling, gaining insights into the early stages of neutron star evolution and the behavior of neutrinos in high-density environments. Another potential feature of neutron stars is the boundary layer between the solid crust and the superfluid core. This boundary layer, where matter transitions from a solid to a superfluid state, plays a crucial role in the star's rotational dynamics and magnetic field behavior. Interactions between the crust and core at this boundary can create friction, affecting the neutron star's rotation and potentially leading to observable phenomena like glitches. Studying this boundary layer is essential for understanding the internal composition of neutron stars, as it reveals how matter behaves at extreme densities where quantum mechanics and nuclear physics converge. The study of timing noise in pulsars adds yet another layer to neutron star research. Timing noise refers to random fluctuations in the pulsar's rotation rate, which creates subtle irregularities in its otherwise precise timing. This noise can be caused by interactions within the neutron star's core, crust, or magnetic field, and studying it helps scientists understand the star's interior dynamics. By analyzing timing noise, researchers can probe the processes occurring deep within neutron stars, revealing how internal changes affect rotation and shedding light on the nature of neutron star cores. Neutron stars are also associated with hadronic matter, which is composed of protons and neutrons that interact through the strong nuclear force. Under the immense pressures within neutron stars, hadronic matter may undergo transformations that produce exotic particles like hyperons, strange quarks, or even deconfined quarks. These transformations are believed to occur at extreme densities where neutrons break down, leading to new forms of nuclear matter. Observing neutron stars with high densities allows scientists to study hadronic matter in ways that are impossible on Earth, pushing the boundaries of nuclear physics and potentially leading to the discovery of previously unknown states of matter. Another fascinating area involves the study of fallback disks around neutron stars. After a supernova explosion, some of the ejected material can fall back toward the neutron star, forming a disk of gas and dust around it. Over time, this fallback material may interact with the neutron star, contributing to its magnetic field and potentially even accreting onto the star's surface. Fallback disks provide a unique environment for studying accretion, the formation of magnetic fields, and the role of supernova remnants in shaping neutron stars. By observing fallback disks, scientists can trace the life cycle of material ejected from supernovae and understand how it influences the evolution of neutron stars. The study of thermal evolution in neutron stars is also of great interest. As neutron stars age, their temperature gradually decreases, but this cooling process depends on a complex interplay of factors, including the star's composition, magnetic field, and accretion history. Measuring the temperature of neutron stars at various ages allows scientists to model their thermal evolution, providing insights into how different factors influence cooling rates. Observing thermal evolution helps researchers understand the life cycle of neutron stars, revealing how these stars change over millions of years and offering clues about their internal structure. In recent research, scientists have also explored the concept of core crust coupling in neutron stars, which describes the interaction between the superfluid core and the solid crust. This coupling is crucial for understanding the rotational dynamics of neutron stars, as any change in one layer can influence the other. For example, when the core shifts due to a superfluid vortex movement, it can trigger a response in the crust, potentially leading to rotational glitches. Studying core crust coupling reveals how different layers of a neutron star interact, offering clues about its composition, density gradients, and rotational stability. Neutron stars also bring us closer to understanding exotic fermionic matter. Fermions, which include particles like protons and neutrons, are subject to the Pauli exclusion principle, preventing them from occupying the same state. In the extreme conditions within neutron stars, fermions may organize into unique configurations, including fermionic condensates or paired states. Observing these configurations helps scientists explore new forms of matter that arise under high density and pressure, revealing quantum behaviors that challenge traditional physics. Lastly, neutron stars contribute to our understanding of the universe's baryonic matter, which includes all matter composed of protons and neutrons. Neutron stars are one of the densest forms of baryonic matter in existence, offering a glimpse into the limits of how this matter behaves under extreme conditions. Studying neutron stars helps scientists understand the distribution and properties of baryonic matter, from the tiniest subatomic particles to the largest cosmic structures. Neutron stars embody the universe's extremes, providing natural laboratories for studying matter, energy, and gravity at their most intense. They continuously unveil insights into the fundamental forces and particles that shape the cosmos, pushing the boundaries of physics and enriching our understanding of the universe. Each discovery about neutron stars is a step into the unknown, reminding us that the cosmos holds boundless mysteries, and that the pursuit of knowledge leads us ever deeper into the vast and intricate tapestry of existence. Continuing further into the enigmatic realm of neutron stars, we encounter the theory of quark stars, a hypothetical type of neutron star where, under immense pressure, the neutrons break down completely into their constituent quarks, creating a new state of matter known as quark matter. In quark stars, quarks move freely, unhindered by the usual confines of protons and neutrons. This state of matter is thought to be incredibly dense and might even represent the true densest form of baryonic matter possible. If quark stars exist, they would bridge the gap between neutron stars and black holes, occupying a unique position in the spectrum of stellar remnants. Discovering a quark star would revolutionize our understanding of matter under extreme pressure, potentially confirming long-standing predictions from quantum chromodynamics and offering direct evidence of quark matter outside high-energy experiments. Another captivating possibility is the presence of color superconductivity within neutron stars. In this theoretical phase, quarks at high densities pair up in ways that allow them to move without resistance, much like electrons in a superconducting material. This behavior could emerge in the superdense core of a neutron star, where conditions are thought to favor such exotic states. Color superconductivity would create magnetic fields far more complex than anything found in ordinary matter, influencing the star's magnetic properties, rotation, and even its cooling rate. Observing indirect signs of color superconductivity in neutron stars would provide insights into the strong nuclear force, one of the four fundamental forces of nature, and reveal how quarks behave under unimaginable densities and pressures. Neutron stars are also linked to the concept of magnetic reconnection, a process where magnetic field lines break and reconnect, releasing large amounts of energy. This phenomenon is common in the Sun, where it drives solar flares, but in neutron stars, magnetic reconnection can occur on a far more intense scale, particularly in magnetars. These reconnection events can cause sudden bursts of X-rays or gamma rays, known as giant flares, that outshine entire galaxies for brief moments. By studying magnetic reconnection in neutron stars, scientists can explore the mechanics of magnetism and plasma physics under extreme conditions, potentially unlocking new knowledge applicable to magnetic fields in stars, galaxies, and even artificial plasma systems on Earth. The possibility of strangelets forming in neutron stars also presents a fascinating avenue for exploration. Strangelets are hypothetical particles composed of up, down, and strange quarks, and they may be more stable than ordinary matter. In theory, if strangelets form within neutron stars, they could spread throughout the star, converting it into a strange star made entirely of strange matter. This process would fundamentally change the star's properties, potentially making it even denser than a typical neutron star. Observing strange stars or strangelets would provide groundbreaking insights into particle physics, as they could represent a new stable form of matter beyond anything found in our current understanding of atomic structure. Neutron stars also challenge us to rethink the idea of isotropic emission, where energy is released uniformly in all directions. Pulsars, for example, emit beams of radiation from their magnetic poles, creating a highly directional emission pattern. In binary systems, however, gravitational effects or the interaction with a companion star can warp or shift these emissions, leading to anisotropic or unevenly distributed radiation. Observing these variations provides insights into the neutron star's magnetic field and its interaction with the surrounding environment, helping scientists model emission behaviors in pulsars and understand how different factors affect the radiation patterns of neutron stars. The study of crustal plate tectonics on neutron stars is another fascinating area. While tectonics on Earth involves the movement of large plates over the planet's mantle, neutron stars might experience shifts and fractures in their crust due to intense magnetic and gravitational forces. These shifts, often referred to as starquakes, can release bursts of energy that we detect as X-rays or gamma rays. By studying the structure and behavior of a neutron star's crust, scientists gain insights into its strength and elasticity, exploring how matter behaves in a solid state under extreme pressure. Understanding crustal movements on neutron stars also provides analogs for studying earthquakes and tectonic processes on Earth and other planets. In the realm of gravitational physics, neutron stars play a key role in studying frame dragging, an effect predicted by general relativity where space-time itself is twisted around a rotating massive object. This phenomenon, also known as the Lense-Thirring effect, is most pronounced near highly compact objects like neutron stars. In binary systems with two neutron stars, frame dragging effects can alter the star's orbits and rotational dynamics in measurable ways. Observing frame dragging around neutron stars offers an extraordinary opportunity to test general relativity under conditions of extreme gravity, allowing scientists to observe one of Einstein's predictions in action. Neutron stars also invite speculation about Planck scale physics, a theoretical realm where quantum mechanics and general relativity converge. At the Planck scale, distances are so small and energies so high that our current physical theories break down, requiring a theory of quantum gravity to fully understand them. Neutron stars, with their intense densities and gravitational fields, are thought to approach conditions close to the Planck scale in their cores. By observing neutron star behavior, scientists hope to glean indirect evidence of physics beyond the standard model, potentially bringing us closer to a unified theory that reconciles gravity with quantum mechanics. The concept of pulsar recycling is another compelling phenomenon in the life cycle of neutron stars. In binary systems, a neutron star can strip material from its companion star, gaining angular momentum and speeding up in the process. This increase in rotation rate transforms the neutron star into a millisecond pulsar, one of the fastest spinning objects in the universe. Pulsar recycling shows how interactions in binary systems can rejuvenate neutron stars, allowing them to shine brightly as pulsars long after they would have otherwise faded. Observing recycled pulsars offers insights into binary star dynamics, the transfer of angular momentum, and the processes that allow neutron stars to maintain high rotation speeds over time. Another area of study focuses on the Eddington limit in neutron stars. The Eddington limit is the maximum luminosity a star can achieve before radiation pressure overcomes gravitational pull, causing it to lose mass. In neutron stars, particularly those in binary systems, this limit is often exceeded during periods of intense accretion, where material falling onto the neutron star creates bursts of radiation. By studying these super Eddington luminosities, scientists can explore how neutron stars handle extreme radiation pressures and accretion rates, providing insights into the physics of high-energy emissions and the stability of stars under intense radiation. The hypothesis of scalar field dark matter interacting with neutron stars is another area of theoretical research. Scalar fields are mathematical constructs used to describe fields of particles like the Higgs boson, and some theories propose that dark matter could consist of scalar field particles. If this form of dark matter interacts with neutron stars, it might affect the star's rotation, magnetic field, or thermal evolution in ways that could be observed from Earth. Detecting scalar field dark matter through its effects on neutron stars would be revolutionary, offering direct evidence of dark matter's influence on baryonic matter and opening new pathways in both astrophysics and particle physics. Neutron stars are also thought to hold potential for quasi-periodic oscillations, QPOs, in their emissions, especially in systems where they interact with an accretion disk. QPOs are fluctuations in the X-ray intensity that repeat over short timescales, believed to result from interactions between the neutron star's magnetic field and the material in the accretion disk. Observing QPOs provides a unique way to probe the neutron star's magnetic field strength, the structure of the accretion disk, and the dynamics of particle movement under extreme gravitational and magnetic influences. QPOs serve as windows into the behavior of matter in high-energy environments and offer clues about the inner workings of neutron star accretion processes. The concept of tidal deformability in neutron stars is another exciting area of study, particularly relevant to binary systems where neutron stars orbit closely. Tidal deformability refers to how much a neutron star's shape is distorted by the gravitational pull of a nearby massive object, like another neutron star or a black hole. This distortion affects the gravitational wave signals emitted during mergers, allowing scientists to infer information about the star's internal structure and composition. Observing tidal deformability provides insights into the behavior of dense matter, helping scientists refine models of neutron star interiors and understand the forces that govern matter at nuclear densities. Finally, neutron stars contribute to the search for ultra-high-energy cosmic rays, particles that arrive on Earth with energies far beyond those achievable in human-made accelerators. Some theories propose that neutron stars, particularly magnetars, could be a source of these cosmic rays, as their intense magnetic fields and rapid rotations provide ideal conditions for accelerating particles to extreme speeds. Observing ultra-high-energy cosmic rays from neutron stars would confirm their role as particle accelerators, revealing the processes that govern cosmic rays and providing clues about the nature of particle acceleration on both stellar and galactic scales. Each new discovery about neutron stars challenges the limits of our understanding, shedding light on the nature of matter, energy, and gravity in conditions far beyond human experience. These remnants of massive stars offer a profound glimpse into the extremes of physics, where the boundaries between known and unknown blur. The study of neutron stars continues to drive the evolution of astrophysics and particle physics, drawing us ever closer to answers about the universe's most profound mysteries and reminding us of the vast, intricate beauty of the cosmos. As we delve further into the enigmatic properties of neutron stars, we reach the captivating concept of neutron star mergers, which produce some of the most energetic events in the cosmos. When two neutron stars spiral into each other and collide, they unleash a tremendous release of energy in the form of gravitational waves, gamma rays, and a cascade of electromagnetic radiation across the spectrum. These mergers, detected as kilonovae, are believed to be the primary source of many of the universe's heaviest elements, including gold, platinum, and uranium. Observing neutron star mergers has opened a new era in multi-messenger astronomy, allowing scientists to detect gravitational waves alongside traditional light-based signals. This combined information reveals not only the dynamics of such collisions, but also the processes responsible for element formation, linking the life cycles of stars to the very materials that compose planets and, ultimately, life itself. Another area of intrigue is the study of hypermagnetic fields and magnetars, an especially powerful type of neutron star with magnetic fields that can reach up to a quadrillion times stronger than Earth's. These hypermagnetic fields are so intense that they distort atomic structures, influencing the behavior of matter itself. Magnetars often produce sudden, violent flares due to shifts in their magnetic fields, releasing energy in bursts of X-rays and gamma rays that can be detected across galaxies. By observing these hypermagnetic fields, scientists can gain a better understanding of the role magnetism plays in extreme environments, revealing the unique conditions under which magnetic forces dominate over other interactions. Magnetar fields also serve as a laboratory for studying quantum electrodynamics, QED, effects, where the interplay between electricity and magnetism occurs at scales unachievable on Earth. In another extraordinary development, neutron stars have provided insights into the R-mode instability, a form of rotational instability that causes oscillations in the star's fluid interior. These R-mode oscillations generate gravitational waves as the star's shape continually shifts, redistributing its rotational energy. The R-mode instability causes the neutron star to lose angular momentum over time, eventually slowing its spin. Observing these oscillations offers a unique opportunity to study gravitational wave emissions over extended periods, providing a continuous source of gravitational waves for detectors on Earth. This research gives scientists a way to explore the inner dynamics of neutron stars, offering indirect glimpses into their core properties and potentially refining models of gravitational wave production. Neutron stars also bring up the fascinating possibility of quantum vortices within their superfluid cores. In the unique conditions inside a neutron star, superfluid matter forms vortices that rotate in sync with the star's overall spin. These quantum vortices are unlike anything we observe in familiar fluids. They follow strict quantum rules, resulting in discrete, stable configurations. When these vortices shift or interact with the crust, they can trigger starquakes or rotational glitches. Studying quantum vortices offers a way to understand superfluidity in a high-density setting, where quantum mechanics governs the behavior of large-scale phenomena, opening new pathways in both quantum mechanics and astrophysics. The exploration of neutron stars has also introduced us to the notion of pasta phases within the crust, named for their resemblance to various pasta shapes, such as lasagna, spaghetti, and gnocchi. These phases describe the structured arrangement of protons and neutrons under immense pressure. In the pasta layer, atomic nuclei align into sheets, tubes, and clumps, creating the densest known configurations of matter before collapsing into a pure neutron core. These structures are thought to influence the thermal and electrical conductivity of neutron stars, affecting how they cool and evolve. Observing signs of pasta phases offers scientists a natural laboratory to study nuclear matter and structural transitions, providing clues about how nuclei interact under extreme conditions. One of the most speculative but intriguing hypotheses surrounding neutron stars is the idea of Planck stars. These theoretical objects are postulated to form when neutron stars approach a critical mass threshold, preventing further collapse into black holes by reaching a state governed by quantum gravity. In a Planck star, the extreme compression reaches the Planck scale, where quantum gravity effects counterbalance gravitational collapse, creating a stable but highly dense object. If Planck stars exist, they would represent a state of matter beyond our current understanding, governed by laws that unify quantum mechanics with general relativity. Observing signs of Planck stars would reveal insights into quantum gravity, potentially transforming our understanding of space-time and the fundamental forces at play in the universe. Neutron stars also shed light on the equation of state, EOS, for ultradense matter, a relationship that describes how matter behaves at extreme pressures and densities. The EOS is crucial for predicting the size, mass, and stability of neutron stars, as well as for understanding their internal structure. Observing variations in neutron star masses and radii helps refine this equation, narrowing down the possible configurations of matter in the cores of these stars. This research is central to nuclear physics, as it addresses fundamental questions about the limits of atomic nuclei and how particles interact under conditions that test the boundaries of known physics. The study of neutron stars has also brought us to the concept of superburst phenomena, intense thermonuclear explosions on the surfaces of neutron stars that far exceed regular X-ray bursts in both power and duration. Superbursts are thought to occur when carbon-rich layers on the star's surface ignite in a runaway nuclear reaction, producing X-rays that can shine for hours. These bursts provide a unique opportunity to study nuclear fusion in ultra-high gravity, helping scientists understand nuclear reaction rates and energy generation in extreme conditions. By observing superbursts, astronomers can probe the outer layers of neutron stars, revealing the processes that govern energy release in some of the most compact objects in the cosmos. Another fascinating phenomenon observed in neutron stars is the gravitational wave recoil that occurs after a neutron star merger. When two neutron stars collide, they release intense gravitational waves that carry momentum away from the system, potentially giving the merged object a kick. This kick can propel the resulting object, a neutron star or black hole, through space at high velocities. Observing gravitational wave recoil events allows scientists to study the momentum transfer in cosmic collisions and provides insights into the final moments of neutron star mergers. These recoils also help researchers understand the movement of compact objects within galaxies, influencing galactic evolution and the distribution of heavy elements. Neutron stars also play a role in cosmic magnetism, influencing the magnetic field structure of entire galaxies. In regions dense with neutron stars and remnants of supernova explosions, magnetic fields can become amplified and organized into complex structures that shape the galactic magnetic field. These interactions contribute to our understanding of how magnetic fields evolve on cosmic scales, providing insights into the processes that govern magnetic field generation and sustainment in galaxies. By studying neutron stars in different galactic environments, scientists can better understand the magnetic history of the universe and the role of compact objects in structuring the cosmos. Another area of neutron star research focuses on conformal symmetry breaking. Conformal symmetry is a concept in physics where objects remain invariant under certain transformations, like scaling. Some theories suggest that, in the ultra-dense conditions of neutron stars, conformal symmetry could be broken, leading to novel interactions and particle behaviors. Observing the effects of conformal symmetry breaking within neutron stars could reveal new fundamental forces or interactions at play, offering insights into uncharted areas of particle physics. Neutron stars are also essential to the study of anisotropic pressure within compact objects. Unlike ordinary stars, neutron stars may experience uneven pressures in different directions due to their strong magnetic fields and the arrangement of matter within them. This anisotropic pressure influences the shape, rotation, and magnetic behavior of the neutron star, affecting its stability and potentially leading to structural deformations. Studying these pressure differences provides valuable data on how matter responds to magnetic and gravitational forces in extreme environments, helping scientists model the behavior of dense, anisotropic matter in other astrophysical settings. One especially promising area of research involves neutron stars and axion detection. Axions are hypothetical particles that could solve the mystery of dark matter and help explain certain symmetry problems in particle physics. Neutron stars, with their high-density environments and magnetic fields, may be able to convert axions into detectable photons, making them a potential natural source for axion detection. Detecting axions around neutron stars would be a revolutionary breakthrough, providing evidence for dark matter and revealing a new class of particles that could reshape our understanding of the universe's composition. The notion of neutron star mountains is another intriguing concept, where minuscule deformations on the neutron star's crust create tiny mountains. Although these deformations are only a few millimeters high, they contain immense mass due to the star's density and could emit continuous gravitational waves as the star rotates. Observing gravitational waves from neutron star mountains would allow scientists to probe the structure of neutron star crusts and gain insights into the behavior of ultradense matter. These mountains also offer a window into the nature of deformable structures in high-gravity environments, providing an analog for studying the stability and flexibility of materials in extreme conditions. Lastly, neutron stars continue to contribute to the study of gamma-ray halos observed in certain galaxies. Some galaxies exhibit extended halos of gamma-ray emissions, and it's believed that neutron stars, particularly pulsars, may contribute to these halos. As pulsars emit high-energy particles, these particles can travel through space, interacting with interstellar material and creating gamma rays that form a diffuse halo around the galaxy. Studying gamma-ray halos and their link to neutron stars enhances our understanding of galactic structures and the role of compact objects in cosmic particle acceleration, showing how neutron stars influence their environments even across vast distances. In every respect, neutron stars offer a boundless landscape of scientific inquiry, where each discovery brings us closer to the fundamental nature of matter, energy, and gravity. They serve as cosmic laboratories for testing our most profound theories, challenging our understanding and expanding the limits of human knowledge. As we continue to observe these stellar remnants, we unlock new dimensions of the universe, each discovery illuminating the extraordinary complexity and beauty of the cosmos, reminding us of the endless mysteries that await in the vastness of space. As we dive even further into the extraordinary world of neutron stars, we reach the concept of exotic core composition, where it's hypothesized that the cores of neutron stars could contain forms of matter we've yet to fully understand or observe. One possibility is the presence of kaon condensates, an exotic phase in which kaons, particles that contain strange quarks, condense in the core under extreme pressure. These kaon condensates would alter the neutron star's density, pressure, and behavior, potentially leading to changes in its mass and radius. Observing evidence of such condensates would provide groundbreaking insights into high-density nuclear physics and the behavior of strange quarks, pushing the boundaries of particle physics. Another remarkable phenomenon linked to neutron stars is the supernova fallback. After a massive star explodes as a supernova, some of the ejected material can be pulled back by the intense gravity of the newly formed neutron star. This fallback material forms a disk around the neutron star, potentially fueling further accretion and magnetic activity. In some cases, supernova fallback can even lead to the formation of a secondary explosion or trigger unusual X-ray emissions. Studying these fallback disks provides insight into the evolution of neutron stars shortly after their formation, as well as the ways in which leftover supernova material interacts with dense remnants. In recent years, scientists have also considered the idea of dark matter capture by neutron stars. According to this theory, neutron stars moving through dark matter-rich regions of space may capture dark matter particles due to their immense gravitational fields. As these particles accumulate in the neutron star's core, they could eventually affect the star's temperature, rotation rate, or internal structure. Detecting changes potentially caused by dark matter interactions within neutron stars would provide a revolutionary approach to understanding dark matter, offering indirect evidence of this elusive substance and providing clues about its properties and role in the universe. Neutron stars are also central to the study of electroweak symmetry breaking under extreme conditions. Electroweak symmetry breaking is a fundamental process in particle physics that gives particles mass, mediated by the Higgs field. In the intense environments of neutron stars, electroweak forces may behave differently, potentially giving rise to phenomena not observed elsewhere. By observing neutron stars, scientists hope to uncover signs of altered electroweak interactions, which could reveal new aspects of particle physics and contribute to our understanding of mass, symmetry, and the forces that shape matter. Another fascinating idea involves the spin-flip events observed in certain neutron stars. In binary systems, neutron stars can sometimes undergo a process called spin flipping, where their rotational orientation changes due to gravitational interactions with a companion star or the accretion of material. This reorientation can affect the timing of the pulsar's emissions and alter its magnetic field dynamics, producing changes observable from Earth. Spin-flip events provide a natural experiment for studying the effects of angular momentum transfer, magnetic field alignment, and the interaction of gravitational and rotational forces under extreme conditions. Neutron stars are also explored as potential sources of cosmic rays in the highest energy ranges. These stars, particularly young, rapidly rotating pulsars and magnetars, can accelerate particles to near-light speeds, creating cosmic rays with energies far beyond what human-made particle accelerators can achieve. By studying the cosmic rays that reach Earth, scientists can trace their origins to neutron stars and gain insights into particle acceleration mechanisms, magnetic field dynamics, and the influence of neutron stars on their surrounding space. The idea of symmetry restoration within neutron stars is yet another topic of theoretical interest. Under extreme pressure and temperature, it's possible that certain symmetries broken in ordinary conditions could be restored within the core of a neutron star. For instance, chiral symmetry, a property related to the arrangement of quarks within protons and neutrons, could be restored in these high-energy environments. Observing signs of symmetry restoration within neutron stars would offer invaluable clues about the fundamental forces of nature, providing a rare look at how matter behaves in a truly primordial state. Neutron stars also serve as natural observatories for studying pair production cascades. When particles in the magnetosphere of a neutron star are accelerated to high energies, they can create electron-positron pairs, leading to a cascade effect where these pairs generate additional particles. This phenomenon is particularly prominent in pulsars and magnetars, where the intense magnetic fields and high-energy environments make pair production highly efficient. Studying these cascades helps scientists understand particle interactions under extreme electromagnetic forces, shedding light on the behavior of matter and antimatter in high-energy settings. One extraordinary hypothesis is that neutron stars might serve as cosmic scales for measuring fundamental constants. Due to their precise timing and stable environments, neutron stars, especially pulsars, allow scientists to test whether physical constants, like the gravitational constant or the fine structure constant, remain unchanged over time and space. By observing neutron stars across various regions of the universe, scientists can test the constancy of these fundamental values, gaining insights into whether the laws of physics are truly universal or if they vary under different cosmic conditions. The presence of cold neutron stars is another area of study. While most neutron stars are initially formed with extremely high temperatures, some may cool rapidly due to processes like neutrino emissions or interactions with exotic particles. These cold neutron stars, which would emit very little thermal radiation, might be difficult to detect through traditional methods but could reveal their presence through gravitational effects or radio emissions. Observing cold neutron stars could help scientists understand the cooling mechanisms of neutron stars and explore how temperature affects the stability and evolution of dense objects. The study of neutron stars has also sparked interest in the potential for mass asymmetry, where the star's mass distribution is uneven, potentially caused by accretion or internal density variations. This asymmetry can create a wobble in the neutron star's rotation, affecting the timing of its pulsations. Observing these variations allows scientists to probe the internal structure of neutron stars, offering clues about their density, composition, and the effects of accretion on their stability. Another extraordinary area of research is the effect of neutron stars on interstellar chemistry. High-energy emissions from neutron stars, such as X-rays and gamma rays, can influence the chemistry of the surrounding space by ionizing gases, breaking molecular bonds, and initiating chemical reactions that wouldn't otherwise occur. In some cases, these interactions could lead to the formation of complex organic molecules. Studying the chemical environments around neutron stars provides insights into the role of these stars in the broader galactic ecosystem, potentially contributing to the chemical diversity of the universe and the conditions that could lead to prebiotic chemistry. Neutron stars also offer a pathway to understanding holographic dualities, a theoretical concept where a lower-dimensional system describes a higher-dimensional phenomenon. Some theories suggest that the intense gravitational fields around neutron stars might exhibit holographic properties, where information about the star's interior could be encoded on its surface or outer regions. Observing these effects would provide groundbreaking evidence for holographic principles, potentially linking quantum mechanics and general relativity in ways that bring us closer to a unified theory of physics. One intriguing aspect of neutron star study involves the tidal locking that can occur in binary systems. In some cases, a neutron star can become tidally locked with its companion, meaning that the same face of the neutron star always points toward the other star, much like the moon is tidally locked with Earth. This tidal locking affects the magnetic and thermal dynamics of the neutron star, as well as the accretion processes if material is being transferred from the companion. By studying tidally locked neutron stars, scientists can explore the gravitational interactions between compact objects and gain insights into the impact of tidal forces on stellar evolution. Another emerging area is the search for boson clouds around neutron stars. Certain dark matter theories predict that bosons, if they exist, could form dense clouds around massive objects like neutron stars. These boson clouds would interact weakly with the neutron star's material, but could create detectable signals, such as subtle changes in the star's rotation or magnetic field. Observing such clouds would provide evidence for a new type of particle, offering clues about dark matter and expanding our understanding of particle interactions in gravitational fields. Neutron stars also contribute to the field of gamma-ray scintillation, where gamma-ray emissions from these stars are scattered by interstellar matter, causing them to flicker or scintillate as they travel to Earth. This scintillation effect allows scientists to map the interstellar medium, revealing the distribution and density of gas and dust along the line of sight to the neutron star. Observing gamma-ray scintillation helps astronomers understand the structure of the galaxy, as well as the effects of interstellar matter on high-energy emissions. Lastly, neutron stars allow scientists to investigate vacuum polarization, a quantum phenomenon where strong magnetic fields cause virtual particle-antiparticle pairs to momentarily pop into existence, altering the properties of the vacuum around the star. This effect is predicted by quantum electrodynamics and can occur in the extreme magnetic fields of magnetars. Observing vacuum polarization near neutron stars provides a direct test of quantum mechanics in strong fields, offering insights into how the vacuum of space behaves under conditions that push the boundaries of known physics. Neutron stars, as cosmic laboratories, continue to astonish scientists, challenging our understanding of physics at every turn. They reveal phenomena that bridge the smallest particles with the largest cosmic structures, from quantum interactions to galactic-scale magnetic fields. Each new discovery about neutron stars unveils a deeper layer of the universe's complexity, inspiring us to explore further and reminding us that the cosmos holds endless mysteries waiting to be unraveled. Expanding our exploration of neutron stars, we delve into the concept of isospin asymmetry within these dense objects, an area that addresses the balance between protons and neutrons in nuclear matter. In most atomic nuclei, protons and neutrons are present in roughly equal numbers, but within neutron stars, this balance shifts dramatically. Isospin asymmetry measures the ratio of neutrons to protons, and in the extreme environments of neutron stars, this asymmetry could lead to unique nuclear configurations. Understanding isospin asymmetry is essential for modeling the equation of state, EOS, of neutron stars, as it directly influences their stability, structure, and even their cooling processes. Research into isospin asymmetry provides a window into nuclear physics under high-density conditions, pushing the boundaries of our knowledge about the strong nuclear force. Another fascinating area involves the potential pentaquark formation within neutron stars. Pentaquarks are exotic particles consisting of 5 quarks, unlike ordinary protons and neutrons, which contain 3. Under the immense pressures in a neutron star's core, it's theorized that quarks could form into these unusual configurations, contributing to an exotic state of matter. Detecting pentaquarks or other exotic particles in neutron stars would offer profound insights into particle physics, revealing how quarks interact under extreme density and potentially leading to the discovery of entirely new forms of matter. The concept of nuclear superfluidity in neutron stars also adds a layer of complexity. Superfluidity, a state of matter where particles flow without resistance, is believed to occur in the cores of neutron stars, where neutrons form a superfluid due to extreme densities and pressures. This superfluidity is theorized to play a critical role in phenomena like rotational glitches, where the superfluid core temporarily transfers angular momentum to the crust. Observing the effects of nuclear superfluidity in neutron stars allows scientists to study this rare quantum state on a macroscopic scale, exploring the properties of superfluid matter and understanding how superfluidity affects rotational dynamics in compact objects. Neutron stars also shed light on the nature of femtonovae, a term coined to describe tiny nuclear reactions that could occur sporadically within a neutron star's crust. In these femtonovae, microscopic regions of the crust experience rapid fusion reactions, generating bursts of localized energy. While these reactions are far smaller than traditional supernovae, they still have significant effects on the neutron star's crust, potentially triggering starquakes or minor changes in magnetic fields. Detecting femtonovae could provide a new perspective on nuclear reactions, revealing the fine-scale interactions that occur under high-density conditions in the crust of neutron stars. Another area of active research involves the study of anisotropic cooling in neutron stars. Unlike ordinary stars, where heat dissipates relatively evenly, neutron stars may exhibit uneven cooling due to magnetic field configurations, crust composition, and superfluid effects in the core. This anisotropic cooling creates temperature variations across the surface, affecting the star's thermal emissions. Observing these variations helps scientists understand the star's internal composition and cooling mechanisms, providing clues about the structure and behavior of matter under extreme pressure and temperature. The study of neutron vortices within neutron stars is yet another fascinating field. In the superfluid core of a neutron star, neutron vortices form as tiny, thread-like structures aligned with the star's rotation. These vortices, which follow quantum rules, play a critical role in the star's rotational dynamics. When these vortices interact with the solid crust, they can cause rotational glitches, where the star's rotation temporarily changes. By studying neutron vortices, scientists can explore superfluidity on a cosmic scale, providing insights into the quantum properties of matter under extreme density and helping us understand how angular momentum is managed within neutron stars. Neutron stars also provide an ideal setting for studying tidal resonances, particularly in binary systems where two neutron stars orbit each other closely. As they spiral toward a merger, gravitational forces create resonances that excite oscillations within each star. These tidal resonances can produce unique gravitational wave signals and influence the distribution of mass in the star's interiors. Observing these resonances not only provides data on neutron star interiors, but also helps scientists refine models of gravitational waves and understand the dynamics of binary systems as they approach catastrophic mergers. The hypothesis of dense dark matter cores within neutron stars presents a particularly intriguing possibility. Some theories propose that dark matter could accumulate in the cores of neutron stars over time, potentially affecting the star's mass, rotation, and thermal properties. If dark matter particles interact with regular matter under extreme pressure, they could form a dense, stable core within the neutron star, influencing its observable characteristics. Detecting signs of dense dark matter cores would provide indirect evidence of dark matter interactions, helping scientists understand this mysterious component of the universe and revealing its behavior under intense gravitational forces. Another exciting area of research is the magnetothermal evolution of neutron stars. Magnetothermal evolution examines how the magnetic field and thermal profile of a neutron star evolve together over time. Magnetic fields influence heat distribution within the star, and as the star cools, its magnetic properties change as well. This evolution affects the star's emissions and rotation, shaping its observable characteristics. Studying magnetothermal evolution provides insights into the life cycle of neutron stars and the relationship between magnetic fields and temperature in extreme environments, helping us understand how these stars change over millions of years. Neutron stars are also involved in the study of heavy ion fusion, a process that may occur in their dense cores. Under intense pressures, atomic nuclei within a neutron star's core could undergo fusion reactions involving heavy ions, producing heavier elements and releasing energy. Unlike typical stellar fusion, which primarily involves hydrogen and helium, heavy ion fusion in neutron stars would involve complex, neutron-rich nuclei. Observing or inferring evidence of such fusion could reveal the unique nuclear processes that occur under ultra-high density conditions, expanding our knowledge of fusion beyond what we can study in laboratories on Earth. Another fascinating phenomenon related to neutron stars is gravitational spin-orbit coupling. In binary systems, where neutron stars orbit a companion object, their gravitational fields interact, creating a coupling effect between their spin and orbital motion. This coupling can lead to precession, where the orientation of the neutron star's spin axis gradually changes over time. Observing gravitational spin-orbit coupling provides valuable data for testing general relativity and understanding the complex gravitational interactions that occur in binary systems, especially as they approach mergers. The potential for gamma-ray flashes from neutron stars is another area of interest. In some cases, neutron stars and binary systems can produce brief, intense flashes of gamma rays due to magnetic interactions or material transfer from a companion. These flashes provide data on the neutron star's magnetic field strength, its interaction with surrounding material, and the processes that generate high-energy radiation in binary systems. Observing gamma-ray flashes allows scientists to study high-energy physics in real time, helping us understand the conditions that lead to gamma-ray production in compact objects. The study of bar-mode instabilities in neutron stars has also gained attention. These instabilities occur when a neutron star's rapid rotation causes it to deform into a bar-like shape, emitting gravitational waves as it oscillates. Bar-mode instabilities are particularly likely in newly formed, rapidly spinning neutron stars, and they produce unique gravitational wave signals that could be detected by observatories on Earth. Observing these instabilities would provide insights into neutron star dynamics, the formation of gravitational waves, and the impact of rotational instabilities on the structure of dense stars. In theoretical physics, neutron stars have been considered in the context of axion clouds, where hypothetical axion particles accumulate around the star. Under certain conditions, these axions could form a cloud around the neutron star, interacting with its magnetic field and producing detectable signals. Observing axion clouds would provide evidence for these elusive particles and offer insights into dark matter, as axions are considered a promising dark matter candidate. Neutron stars, with their unique environments, may serve as natural laboratories for detecting and studying axions, pushing the boundaries of particle physics. Neutron stars also contribute to our understanding of Lorentz violating effects, which would occur if the fundamental symmetry of Lorentz invariance, the idea that the laws of physics are the same for all observers regardless of their velocity, is violated under extreme conditions. The intense gravitational and magnetic fields of neutron stars create conditions where Lorentz violating effects might become apparent, providing an opportunity to test the limits of this foundational principle of physics. Detecting any deviations from Lorentz invariance would challenge the current framework of physics, suggesting new interactions or forces at play in the universe. The phenomenon of density oscillations in neutron stars is another intriguing area of study. In their dense cores, neutron stars may experience periodic fluctuations in density, producing waves that travel through the star's interior. These oscillations could affect the star's rotation, magnetic field, and thermal properties, and they may even produce detectable gravitational waves. Observing density oscillations would provide insights into the composition of neutron stars, revealing how matter behaves under intense pressure and giving scientists a way to probe the star's core structure indirectly. Finally, neutron stars offer a unique setting for studying nucleon pairing in high-density environments. Nucleons, protons, and neutrons can pair up in specific configurations under high pressure, forming a state similar to Cooper pairs in superconductors. This pairing affects the thermal and magnetic properties of the neutron star, and influences its cooling and rotational dynamics. Studying nucleon pairing provides insights into nuclear interactions in dense matter, helping scientists understand how the strong nuclear force operates in one of the most extreme settings in the cosmos. Each discovery in the study of neutron stars deepens our understanding of the universe, revealing the complexity and beauty of matter under conditions that push the limits of physics. As natural laboratories, neutron stars continue to offer insights into quantum mechanics, general relativity, and nuclear physics, serving as windows into the most fundamental properties of matter and energy. The mysteries of neutron stars inspire continued exploration, reminding us that the universe holds countless wonders that lie beyond the reach of current knowledge, waiting to be uncovered. Continuing deeper into the mysteries of neutron stars, we arrive at the intriguing concept of quantum chromodynamics, QCD, phase transitions. Quantum chromodynamics, the theory describing the interactions between quarks and gluons, suggests that under extreme conditions, such as those in neutron star cores, matter could undergo a phase transition into a new state. In neutron stars, this QCD phase transition might transform the core into a quark-gluon plasma, a state thought to resemble the matter just after the Big Bang. Observing evidence of QCD phase transitions in neutron stars would unlock insights into the early universe and reveal how fundamental particles interact under intense pressures and temperatures. Detecting these transitions would also provide critical data for modeling the behavior of matter at the smallest scales, offering a deeper understanding of the strong nuclear force. Another fascinating area of study is strange matter seeding. According to certain theories, if strange matter, a stable form of quark matter containing strange quarks, exists within a neutron star, it could spread and seed other parts of the star, potentially converting the entire star into a strange star. This transformation would drastically alter the neutron star's properties, making it denser and more stable than conventional neutron stars. If strange matter is indeed stable and can spread, it could even have implications for other forms of matter in the universe. Observing such a process would confirm the existence of strange matter and provide a new perspective on the diversity of stellar remnants. The concept of nuclear pasta conductivity in neutron stars adds another layer of complexity. The nuclear pasta phase, where matter is organized into dense, structured shapes like sheets, tubes, and blobs, influences how heat and electricity move through the star's crust. The unique structure of nuclear pasta could impact the thermal evolution and magnetic field behavior of neutron stars, altering how they cool and emit radiation. Studying conductivity in these phases could reveal insights into the behavior of electrons and nuclei under ultra-dense conditions, advancing our knowledge of both nuclear physics and the thermal dynamics within neutron stars. In recent years, neutron stars have also been proposed as sites for studying supersolid phases. Supersolidity is an exotic quantum state where matter exhibits both solid and superfluid properties simultaneously, allowing it to flow without friction while maintaining a rigid structure. Scientists theorize that in the intense environments within neutron stars, certain components of the star's crust or core might enter a supersolid state. Detecting evidence of supersolidity in neutron stars would provide a natural laboratory for this quantum phase and reveal how matter behaves under extreme pressures, combining properties usually associated with vastly different states. The study of magnetorotational instabilities, MRI, in neutron stars presents another intriguing research avenue. MRI is a process that occurs when a rotating magnetic field interacts with surrounding matter, creating instabilities that can transfer angular momentum and amplify magnetic fields. In the dense environments of neutron stars, these instabilities could contribute to their spin-down rates, influence the structure of magnetic fields, and even produce sudden changes in rotation, such as glitches. Observing magnetorotational instabilities would help scientists understand the interaction between rotation and magnetism, offering insights into stellar evolution and the behavior of magnetic fields under extreme conditions. The idea of boson condensates in neutron star cores is another area of exploration. In certain scenarios, bosons, particles that can occupy the same quantum state, might form a condensate within a neutron star, creating a coherent field that influences the star's thermal and magnetic properties. If bosons like axions or other exotic particles form condensates in neutron stars, they could affect the star's cooling rate, magnetic field, and emissions. Detecting evidence of boson condensates would provide groundbreaking insights into particle physics and potentially offer a window into dark matter interactions in one of the universe's most intense environments. Neutron stars also raise questions about R-process nucleosynthesis in kilonovae. When two neutron stars merge, they create conditions ideal for rapid neutron capture, or the R process, which produces many of the heavy elements in the universe. This process is essential for the formation of elements like gold, platinum, and uranium. Observing R-process nucleosynthesis in kilonovae helps scientists understand the origins of these elements, tracing the cosmic journey from neutron star mergers to the distribution of heavy elements across the universe. It also provides insights into the role of neutron stars in the chemical evolution of galaxies. The phenomenon of gravitational spin-orbit resonance in neutron star binaries is another captivating area of research. In close binary systems, gravitational interactions between the neutron stars can create resonances that cause their spin axes to precess, or wobble, in synchrony with their orbits. This resonance affects the timing of pulsar emissions, the production of gravitational waves, and the evolution of the binary system itself. Observing spin-orbit resonances provides a natural testbed for general relativity, offering a rare opportunity to study how strong gravitational forces influence the dynamics of compact objects in binary orbits. Neutron stars also introduce the potential for studying macroscopic quantum coherence in extreme environments. In quantum mechanics, coherence refers to the property where particles behave in a synchronized way, typically observed in small-scale systems like atoms. However, within the superfluid core of a neutron star, neutrons might exhibit macroscopic quantum coherence, forming a unified quantum state on a stellar scale. Observing evidence of macroscopic coherence in neutron stars would provide a unique insight into quantum mechanics on a massive scale, bridging the worlds of quantum theory and astrophysics. The concept of anisotropic pressure gradients in neutron stars is yet another field of study. In normal stars, pressure is generally isotropic or evenly distributed. However, in neutron stars, magnetic fields, rotational forces, and density variations could create anisotropic or uneven pressure gradients. These gradients influence the star's shape, rotation, and magnetic field configuration, impacting its stability and emissions. By studying anisotropic pressures, scientists gain insights into how matter behaves under competing forces in extreme environments, providing clues about the balance of forces in compact objects. In theoretical physics, neutron stars are also considered for testing the existence of higher-dimensional gravity effects. Some theories of quantum gravity suggest that additional spatial dimensions could become noticeable under extreme gravitational conditions, such as those near neutron stars. Observing subtle deviations from general relativity around neutron stars could provide indirect evidence of higher dimensional effects, hinting at a more complex structure of space-time than previously understood. This research could revolutionize our understanding of gravity and reveal new layers of reality that are hidden under ordinary conditions. The study of pulsar wind nebulae, PWN, around neutron stars adds another fascinating aspect to their exploration. When neutron stars emit high-energy particles, these particles interact with the surrounding interstellar medium, creating a glowing nebula of particles known as a pulsar wind nebula. These nebulae serve as natural laboratories for studying particle acceleration, magnetic field interactions, and cosmic ray production. Observing PWNs around neutron stars provides insights into the energetic processes that govern particle behavior in space, as well as the impact of neutron stars on their surrounding environment. The heat transport mechanisms within neutron stars is yet another area of research. Heat transport in neutron stars is influenced by the composition of the crust, superfluid effects, and magnetic fields, creating unique patterns of temperature distribution across the star's surface. Studying these mechanisms helps scientists understand how heat flows through dense, high magnetic field environments, providing insights into thermal dynamics in a setting vastly different from any on Earth. This research also reveals details about the cooling processes of neutron stars and the role of thermal evolution in their life cycles. Neutron stars also provide a way to study gamma-ray polarimetry, the measurement of gamma-ray polarization emitted by these objects. Polarization gives clues about the processes that produce gamma rays, particularly in magnetars and pulsars where intense magnetic fields influence the emission. Observing gamma-ray polarization allows scientists to analyze the alignment and structure of magnetic fields and particle interactions within neutron stars, shedding light on the fundamental mechanisms behind gamma-ray production in high-energy environments. Lastly, neutron stars offer a unique perspective on the idea of self-interacting dark matter, SIDM. In some models of dark matter, particles are thought to interact weakly with one another. In neutron stars, dark matter could accumulate and, if self-interacting, might influence the star's mass, density, and emissions. Observing neutron stars in regions with high dark matter density could provide clues about SIDM, helping scientists explore a potential new form of dark matter and understand its role in cosmic evolution. Each of these areas of research highlights how neutron stars continue to expand the frontiers of physics, astronomy, and cosmology. These compact objects act as portals into the most extreme conditions imaginable, revealing the complex interplay of fundamental forces and challenging our theories about matter, energy, and gravity. Through the study of neutron stars, we gain profound insights into the nature of the universe, discovering ever more intricate layers of reality and confirming that our cosmic journey has only just begun. As we push further into the mysteries of neutron stars, we encounter the concept of neutron star crust fracturing, a phenomenon driven by the intense magnetic and gravitational forces acting on the crust. Over time, these forces create immense stress, eventually leading to fractures or crust quakes that release bursts of energy. These fractures can produce detectable X-rays or gamma rays, illuminating the star's surface and potentially influencing its magnetic field. Studying crust fracturing provides insights into the strength and composition of neutron star crusts, helping scientists understand how solid matter behaves under extreme pressure and magnetic stress. Another compelling area is the study of gravity-induced quantum tunneling within neutron stars. Quantum tunneling, where particles pass through barriers they typically wouldn't overcome, could theoretically occur within neutron stars under the influence of intense gravitational fields. In neutron stars, this tunneling might allow neutrons to penetrate the dense nuclear matter of the core, possibly creating exotic particles or altering the star's core composition. Observing or modeling such tunneling effects could provide a unique view into quantum behavior under strong gravity, revealing how fundamental particles behave in conditions that combine the extremes of both quantum mechanics and general relativity. The possibility of protoneutron stars sheds light on the earliest moments of neutron star formation. Protoneutron stars are formed immediately after a supernova explosion and exist in a transitional state before fully stabilizing into neutron stars. During this phase, they are extremely hot and may emit copious amounts of neutrinos as they cool and contract. Studying protoneutron stars gives scientists a glimpse into the evolution of neutron stars in their infancy, offering insights into the processes that govern their formation, the initial structure of the star, and the influence of rapid cooling on their development. Neutron stars also bring us to the concept of axial symmetry breaking, where the star's shape or magnetic field deviates from symmetry around its rotational axis. This breaking of symmetry can cause unique gravitational wave signatures and influence how the star emits radiation. Axial symmetry breaking may be caused by magnetic field interactions, accretion from a companion, or internal density variations. Observing asymmetries in neutron stars provides valuable data on how matter behaves under uneven forces, giving clues about magnetic field alignment, mass distribution, and the conditions that lead to rotational instabilities. Another area of focus is neutrino trapping within neutron stars. During the formation of a neutron star, especially in protoneutron stars, neutrinos are generated in vast quantities. However, under intense densities, these neutrinos can become trapped within the star, unable to escape immediately. This trapping affects the star's cooling rate and the distribution of thermal energy within it. Studying neutrino trapping helps scientists understand how neutrinos interact with dense matter and the role they play in the thermal evolution of neutron stars, shedding light on cooling mechanisms in environments far beyond those on Earth. The study of mass-radius relationships in neutron stars is another area of research critical to understanding the equation of state, EOS, for dense matter. By measuring the mass and radius of neutron stars, scientists can narrow down possible models for the EOS, which describes how matter behaves under extreme pressure. Each observation of a neutron star's mass-radius relationship adds to our understanding of its internal structure, providing essential data for nuclear physics and helping scientists understand the maximum density matter can achieve before collapsing into a black hole. Another intriguing concept is kinetic heating in neutron stars, especially in binary systems. As material from a companion star accretes onto the neutron star, frictional forces can generate heat in the outer layers of the neutron star, causing localized temperature increases. This kinetic heating can produce unique X-ray emissions that reveal the properties of the accreting material and the magnetic field configuration of the neutron star. Observing kinetic heating allows scientists to study accretion processes, magnetic interactions, and how neutron stars gain energy through interactions with companion stars. The theory of quasi-normal modes in neutron stars also offers valuable insights. Quasi-normal modes are vibrations that occur within neutron stars as a result of gravitational or magnetic disturbances, causing the star to oscillate in specific patterns. These oscillations produce gravitational waves that can carry information about the star's internal structure, density distribution, and equation of state. Observing quasi-normal modes in gravitational wave signals allows scientists to listen to neutron stars, providing an innovative method to study their interiors and refining our models of dense matter physics. The study of diffusion layers in neutron stars adds another dimension to our understanding of their structure. As matter within neutron stars is subjected to intense pressure and temperature, particles can migrate or diffuse from one layer to another over time. This diffusion process affects the star's composition and cooling rate and can influence the magnetic field distribution. By studying diffusion layers, scientists gain insights into how matter behaves at nuclear densities and the long-term evolution of neutron stars as they age. The concept of supernova fallback accretion in neutron stars is also an area of interest. After a supernova explosion, some of the ejected material may fall back onto the newly formed neutron star, creating an accretion disk and potentially altering the star's mass and spin. This fallback material can contribute to the magnetic field strength and create a secondary burst of X-rays as it is accreted. Observing supernova fallback in neutron stars allows scientists to study the aftermath of supernovae and understand the role of fallback material in the evolution of young neutron stars. Spin equilibrium states in neutron stars, particularly in accreting binary systems, offer yet another area of exploration. As neutron stars accrete material from companion stars, they gain angular momentum, which can increase their rotational speed. However, at a certain point, the outward radiation pressure from the neutron star can balance the inward accretion flow, creating a spin equilibrium state where the star's rotation stabilizes. Observing these equilibrium states provides insights into the delicate balance of forces in accreting systems and offers clues about the long-term evolution of rotation rates in neutron stars. Neutron stars are also significant in the study of inelastic collisions of particles within their cores. In the superdense core, particles collide with such high energy that they may undergo inelastic interactions, leading to the formation of exotic particles or new nuclear states. Studying these collisions indirectly through observational data helps scientists understand how nuclear matter behaves in one of the densest environments in the universe, providing insights into particle physics and the potential existence of unknown nuclear states. The concept of core envelope coupling in neutron stars is also essential for understanding their rotational dynamics. The core and outer layers, or envelope, of a neutron star may rotate at slightly different rates due to friction and magnetic interactions. This core envelope coupling can influence the star's overall rotation, affecting its pulsar timing and magnetic field behavior. Studying this coupling provides insights into the internal structure of neutron stars, revealing how angular momentum is distributed and how different layers of the star interact. In the realm of quantum mechanics, neutron stars also allow scientists to explore quantum entanglement under gravity. Neutron stars create intense gravitational fields, and studying how entangled particles behave in such an environment could provide insights into the effects of gravity on quantum states. Observing quantum entanglement in neutron stars, even indirectly, would offer a new perspective on the interface between quantum mechanics and general relativity, potentially leading to breakthroughs in our understanding of both fields. Magnetic reconnection-driven auroras on neutron stars add yet another fascinating area of study. While auroras on Earth are caused by solar wind particles interacting with our planet's magnetic field, neutron stars could experience similar phenomena on a much larger scale. Magnetic reconnection events on neutron stars can accelerate particles along magnetic field lines, creating auroras that emit X-rays or gamma rays instead of visible light. Observing these neutron star auroras provides data on particle acceleration and magnetic field interactions in extreme environments, offering a cosmic analogy to the auroras we observe on Earth. Lastly, neutron stars are valuable in the study of scalar tensor theories of gravity, which extend general relativity by adding scalar fields that could modify gravitational interactions. In the extreme gravitational fields of neutron stars, scalar tensor theories predict subtle deviations from standard general relativity. By carefully measuring the properties of neutron stars, especially in binary systems, scientists can test these theories and potentially uncover new aspects of gravity that are not apparent in weaker gravitational environments. Each of these concepts highlights the unparalleled richness of neutron stars as natural laboratories. They challenge the boundaries of physics, revealing the complex interactions between gravity, quantum mechanics, nuclear forces, and magnetic fields. The study of neutron stars continues to expand our understanding of the universe, pushing us closer to answers about the fundamental nature of matter, energy, and space-time, and reminding us of the profound mysteries that still await exploration in the cosmos. Diving even deeper into the world of neutron stars, we encounter the concept of strange quark matter droplets, tiny concentrations of strange quarks that might form under extreme pressures in neutron stars. Strange quark matter, a proposed state containing up, down, and strange quarks, could appear as stable droplets within the core. If these strange quark droplets exist, they might interact with ordinary nuclear matter in unexpected ways, potentially converting surrounding matter into strange matter and gradually transforming the star's core. Detecting signs of strange quark droplets would provide a direct test of exotic matter theories, helping scientists explore particle behaviors that challenge our understanding of stable matter configurations. The phenomenon of supermassive neutron stars also pushes our knowledge of stellar limits. In theory, neutron stars are capped at around 2 to 3 times the Sun's mass before collapsing into black holes. However, recent discoveries of unusually massive neutron stars suggest that under certain conditions, such as high rotation rates or unknown particle interactions, neutron stars might exceed this threshold, temporarily resisting collapse. Observing supermassive neutron stars helps scientists refine the equation of state for dense matter and explore the true upper mass limits for neutron stars, providing clues about the nature of neutron degeneracy pressure and the potential for new phases of matter in ultradense cores. Another captivating topic is the idea of multi-layer magnetic fields within neutron stars. Unlike Earth, which has a relatively uniform magnetic field, neutron stars may have complex magnetic layers, with each layer exhibiting distinct strengths and orientations. These layered magnetic fields could arise from different phases of star formation, accretion, or internal restructuring. Multi-layer magnetic fields would impact the neutron star's emissions, rotational stability, and even the occurrence of magnetic reconnection events. Observing these layers provides insights into magnetic field evolution, stability, and the long-term changes in neutron stars' magnetic and rotational behavior. The study of photon splitting in neutron stars brings us to the realm of quantum electrodynamics under extreme magnetic fields. In the presence of intense magnetism, photons, particles of light, may split into 2 lower-energy photons, a phenomenon predicted by QED but not observed directly on Earth. The extreme magnetic fields of neutron stars, especially magnetars, could create the perfect conditions for photon splitting, producing unusual radiation signatures. Detecting photon splitting would confirm a key prediction of QED and deepen our understanding of light-matter interactions in high magnetic fields, revealing new aspects of quantum theory. Neutron stars are also vital in exploring gravitational lensing within dense star clusters. When neutron stars reside in dense stellar environments, their gravitational fields can lens light from nearby stars, creating distorted or magnified images. These lensing events provide a natural way to study the mass distribution within neutron stars and to detect hidden neutron stars and star clusters. Observing gravitational lensing caused by neutron stars in dense regions helps astronomers map stellar distributions, understand gravitational interactions on small scales, and test general relativity in dense stellar environments. The phenomenon of temperature gradients on the surface of neutron stars adds another layer to their study. Temperature variations across a neutron star surface can be influenced by magnetic fields, crust composition, and thermal conductivity. These gradients result in uneven X-ray or gamma-ray emissions, giving scientists clues about the star's magnetic field structure, cooling processes, and crustal properties. By analyzing surface temperature maps, scientists can reconstruct the star's thermal history and understand the underlying factors that shape its energy output. Oscillating magnetospheres in neutron stars introduce yet another fascinating area of research. Neutron stars have magnetospheres filled with charged particles influenced by the star's intense magnetic fields. In some cases, these magnetospheres can oscillate, causing changes in particle distribution and emission patterns. These oscillations may be driven by internal magnetic field changes, crustal movements, or interactions with nearby objects. Studying oscillating magnetospheres allows scientists to explore magnetohydrodynamic (MHD) effects in high-energy environments, offering insights into particle acceleration and magnetic field behavior around compact stars. The hypothesis of neutron star planets expands our understanding of planetary formation in extreme environments. Neutron stars, particularly those in binary systems or with fallback disks, may capture or retain planetary bodies. These planets would exist in environments with intense radiation and gravitational forces, leading to unique atmospheric, magnetic, and orbital properties. Observing such planets could reveal how planetary systems form and survive in extreme conditions, offering a new perspective on planetary diversity in the universe. Another intriguing area of study is the effect of time dilation on pulsar emissions. Due to the immense gravitational fields of neutron stars, time dilation causes clocks near them to tick slower compared to distant observers. This effect influences the timing of pulsar emissions, causing slight delays and shifts detectable from Earth. Analyzing time dilation in pulsar signals provides precise tests of general relativity, as well as insights into the neutron star's gravitational field strength and rotational behavior. This research contributes to our understanding of how gravity affects time and offers real-world applications for precision timing and navigation in space. The concept of rotation-induced shape deformation in neutron stars is also significant. As neutron stars spin, centrifugal forces distort their shapes, making them slightly oblate. Rapidly rotating neutron stars experience greater deformation, and this shape change can affect their gravitational wave emissions, magnetic field alignment, and rotational stability. Observing shape deformations in neutron stars allows scientists to study the balance between rotational forces and gravity, providing insights into stellar structure and the limits of rotation in compact objects. Neutron stars also offer insights into antimatter generation in high-energy environments. In the intense magnetic and gravitational fields of neutron stars, particle collisions and accelerations can create conditions where matter and antimatter pairs, such as electron-positron pairs, are produced. This process contributes to high-energy emissions and may influence the surrounding space. Observing antimatter generation in neutron stars sheds light on particle physics, allowing scientists to study matter-antimatter interactions in extreme settings and providing clues about antimatter distribution in the universe. The study of neutron star convective layers is another emerging field. Some models suggest that the outer layers of neutron stars may exhibit convective behavior, where heat is transported outward by the movement of material, similar to convection in stars like the Sun. This convection would affect the neutron star's cooling rate, surface temperature, and even its magnetic field distribution. Observing convective behavior in neutron stars would provide insights into energy transfer mechanisms in dense objects and offer a unique comparison to convection in more familiar stellar environments. Microlensing by neutron stars represents a new method for detecting these objects in the galaxy. When a neutron star passes in front of a background star, its gravitational field can magnify the light from the star, creating a temporary brightening. This microlensing effect is subtle but detectable and provides a way to locate neutron stars that might not emit enough radiation to be seen directly. Observing neutron star microlensing events helps scientists map the distribution of neutron stars in the galaxy and offers a new method for studying compact objects that are otherwise difficult to detect. Neutron stars also contribute to the exploration of quantum anomalies in strong fields. In quantum field theory, certain symmetries can break down in strong fields, creating anomalies where unexpected particle behaviors arise. The extreme magnetic fields around neutron stars, especially magnetars, might create conditions where quantum anomalies become observable, affecting particle interactions and radiation. Detecting these anomalies would provide a unique test of quantum field theory, helping scientists understand particle behavior under conditions unattainable in terrestrial labs. The phenomenon of neutron star precession provides another avenue for studying rotational dynamics. Precession is the gradual change in the orientation of a rotating object's axis, often caused by gravitational or magnetic interactions. In neutron stars, precession can result from binary interactions, crustal movements, or even rotational instabilities, leading to variations in pulse timing and beam orientation. Observing precession in neutron stars allows scientists to study the influence of external forces on rotational stability, giving insights into the star's structure, composition, and magnetic field. Lastly, neutron stars provide a framework for exploring Lorentz-violating dark matter interactions. In certain theories, dark matter might exhibit Lorentz-violating interactions, where the usual laws of physics are altered in specific ways. Neutron stars, with their dense gravitational fields, are ideal environments for testing such theories. Detecting deviations in neutron star behavior that suggest Lorentz-violating dark matter interactions would have profound implications for both astrophysics and fundamental physics, potentially unveiling new aspects of the universe that challenge conventional understanding. Each of these research areas illustrates how neutron stars continue to surprise and intrigue scientists, revealing phenomena that bridge the gap between the quantum and cosmic scales. Through neutron stars, we gain insights into the extremes of physics, from particle interactions and quantum states to gravitational dynamics and stellar evolution. These compact objects, remnants of once massive stars, remain essential to our quest to understand the universe, offering endless opportunities to probe the deepest mysteries of matter, energy, and space-time. Continuing our journey into the depths of neutron star phenomena, we encounter the concept of quark-hadron continuity, a theory suggesting that under certain conditions, matter could exist in a transitional phase between quarks and hadrons. In neutron stars, where densities are exceptionally high, it's theorized that quarks may begin to deconfine from protons and neutrons without fully transitioning to a quark-gluon plasma. This continuity between quark matter and hadronic matter would be a unique state, offering clues about the strong force at work in extreme environments. Observing signs of quark-hadron continuity would deepen our understanding of the transition between ordinary matter and quark matter, bridging particle physics with astrophysical conditions. Another fascinating area of research involves free precession in neutron stars, a phenomenon where the star's rotation axis wobbles independently of its magnetic axis. This precession causes the direction of the pulsar beam to shift over time, altering how its pulses appear from Earth. Free precession could result from asymmetries in the star's internal structure, crustal stress, or even interactions with magnetic fields. Observing free precession provides insights into the internal structure of neutron stars and the factors that affect their rotational dynamics, giving scientists a chance to study the complex interactions between the star's core, crust, and magnetic field. The concept of dark photon emission from neutron stars is another area of speculative but exciting research. Dark photons, hypothetical particles associated with a potential dark sector of physics, could interact weakly with ordinary matter and be produced in environments with high densities and magnetic fields, such as neutron stars. If neutron stars emit dark photons, they could create detectable signals as these particles decay or interact with other particles in space. Detecting dark photon emissions would open a new window into dark matter research, providing evidence for the existence of dark sector particles and revealing their potential role in astrophysical processes. Neutron stars are also valuable for studying fast magnetoacoustic oscillations, which are waves that propagate through the star's magnetosphere due to interactions between magnetic fields and charged particles. These magnetoacoustic waves can influence the pulsar's emission, particle acceleration, and radiation patterns. By studying these oscillations, scientists can gain insights into the star's magnetic field structure, particle dynamics, and the behavior of plasma in extreme conditions, helping to refine models of magnetospheric activity and magnetic field interactions. The theory of pulsar timing noise as a probe of dark matter introduces an innovative method for studying dark matter. Pulsar timing noise, the subtle fluctuations in pulsar rotation rates, could potentially be influenced by the gravitational effects of dark matter clumps or substructures. If these clumps pass near a pulsar, they could create measurable shifts in timing. Analyzing these shifts provides a novel way to map the distribution of dark matter in the galaxy, using neutron stars as natural detectors of dark matter's gravitational influence. Another intriguing topic is the Hyperon puzzle, which addresses the unexpected stability of neutron stars despite the presence of hyperons, exotic particles that contain strange quarks. In theory, hyperons should form at the high densities in neutron star cores, reducing the pressure needed to support the star and leading to a collapse. However, the existence of massive neutron stars suggests that there are forces at play preventing this collapse, possibly related to repulsive interactions between hyperons or unknown forces at nuclear densities. Solving the Hyperon puzzle would provide insights into the behavior of strange quarks, nuclear forces, and the internal composition of neutron stars. The study of pulsar glitches and anti-glitches provides another layer to understanding rotational dynamics in neutron stars. Glitches are sudden increases in rotation rate, often attributed to interactions between the crust and superfluid core. Anti-glitches, in contrast, are abrupt decreases in rotation. These events reveal the intricate relationship between a neutron star's different layers and the forces acting within. Observing and modeling these glitches helps scientists probe the star's interior, especially the properties of the superfluid core and its coupling to the solid crust. In the field of quantum mechanics, neutron stars are relevant for exploring quantum decoherence in strong gravitational fields. Quantum decoherence, where quantum systems lose their coherent state, could be influenced by intense gravity near neutron stars. Studying the impact of gravitational fields on decoherence would provide a bridge between quantum mechanics and general relativity, revealing how quantum information behaves under extreme conditions. If decoherence behaves differently in neutron stars, it could offer insights into the fundamental nature of quantum information and the possible quantum structure of gravity. The concept of neutron star crust superfluidity also enriches our understanding of quantum states in dense matter. In neutron star crusts, certain layers may exhibit superfluid properties, where neutrons flow without resistance. This crustal superfluidity could impact the star's cooling, glitch behavior, and rotational stability. Observing signs of crust superfluidity provides a natural laboratory for studying superfluid phases in dense, low-temperature environments, revealing how superfluidity affects large-scale structures under extreme conditions. The hypothesis of scalar field clouds around neutron stars introduces a new approach to testing scalar field theories. Scalar fields, often considered in theories of modified gravity or dark energy, could form clouds around neutron stars under specific conditions. These clouds would interact weakly with the neutron star's gravitational and electromagnetic fields, potentially producing detectable gravitational wave signals or timing shifts in pulsar emissions. Detecting scalar field clouds would provide evidence for scalar field theories and contribute to our understanding of gravity's behavior in strong field environments. Neutron stars are also essential to the study of R-mode instability saturation, a rotational instability where certain oscillation modes grow in amplitude, emitting gravitational waves as they do. This R-mode instability could eventually reach a saturation point, where internal forces counteract the oscillation growth, stabilizing the star's rotation. Observing R-mode instabilities and their saturation helps scientists understand how neutron stars lose rotational energy through gravitational waves, providing a unique perspective on angular momentum loss and the mechanisms that stabilize rotating compact objects. The potential existence of neutron star atmospheres provides another area of interest. Some neutron stars may have thin atmospheres composed of exotic particles or ions from the star's crust. These atmospheres would influence the star's thermal emissions, spectral lines, and X-ray luminosity. Observing neutron star atmospheres provides clues about surface composition, magnetic field effects, and particle behavior in high-gravity environments, offering a window into the conditions at the very boundary of the neutron star surface. The concept of magnetic vortices in rotating neutron stars brings us to the study of quantum magnetism on a massive scale. In superfluid neutron stars, magnetic vortices are created as the star rotates, aligning with the rotation axis and influencing the magnetic field configuration. These vortices could contribute to the neutron star's magnetic behavior, influencing how it emits radiation and interacts with surrounding material. Studying magnetic vortices in neutron stars allows scientists to explore quantum magnetism and rotational dynamics, bridging the gap between quantum mechanics and large-scale astrophysical phenomena. The Pauli exclusion principle in neutron stars offers insights into particle physics under extreme conditions. This principle, which states that no two fermions can occupy the same quantum state, is responsible for the degeneracy pressure that supports neutron stars against gravitational collapse. Observing how the Pauli exclusion principle operates in neutron stars provides a large-scale demonstration of quantum mechanics, showing how fundamental principles govern the structure and stability of massive objects. This research deepens our understanding of how quantum effects scale up to astronomical sizes, helping scientists explore the universality of quantum mechanics. Neutron stars are also relevant for testing spontaneous symmetry breaking in dense environments. Spontaneous symmetry breaking, a process in which a system transitions from a symmetric state to an asymmetric one, could occur within neutron stars due to intense pressure and particle interactions. This breaking of symmetry could influence the star's magnetic fields, rotational stability, and particle behavior. Detecting signs of spontaneous symmetry breaking would help scientists understand how symmetry plays a role in the structure of dense matter, providing a window into fundamental particle interactions. The phenomenon of anomalous X-ray pulsars, AXPs, introduces a type of neutron star that emits X-rays without the typical pulsar mechanisms. These AXPs are thought to be magnetars, neutron stars with exceptionally strong magnetic fields, emitting X-rays due to magnetic decay rather than rotation. Observing AXPs provides insights into the diversity of neutron star emissions and the role of magnetic field decay in producing high-energy radiation. Studying these X-ray pulsars offers a deeper understanding of how extreme magnetism drives neutron star behavior. Lastly, neutron stars provide a framework for exploring modified inertia effects in strong gravitational fields. In modified inertia theories, inertial mass varies with gravitational potential, predicting different motion patterns in strong fields. Neutron stars, with their intense gravitational fields, offer a natural test for these theories. Observing deviations in neutron star motion could provide evidence for modified inertia, offering an alternative explanation for gravitational behavior in compact objects and potentially reshaping our understanding of inertia in high-density environments. These areas illustrate the profound insights neutron stars provide into the frontiers of physics. Through their study, scientists are uncovering the interplay of quantum mechanics, nuclear forces, and general relativity on astronomical scales, challenging and expanding our understanding of the universe. Neutron stars, as cosmic laboratories, continue to be essential in our pursuit of the fundamental laws that govern matter, energy, and space-time, unveiling mysteries that shape the very fabric of reality. As we delve even further into the depths of neutron star science, we come across the phenomenon of X-ray polarimetry, which involves studying the polarization of X-rays emitted by neutron stars, particularly magnetars and pulsars. X-ray polarimetry can reveal details about the magnetic field structure, geometry, and radiation mechanisms of neutron stars, as polarization provides information about how magnetic fields interact with particles in extreme environments. By analyzing polarized X-rays, scientists can gain insights into the behavior of charged particles and magnetic fields under high-energy conditions, potentially confirming predictions from quantum electrodynamics, QED, and magnetohydrodynamics, MHD, about light and particle interactions in ultramagnetic fields. The theory of pre-supernova star mergers involving neutron stars is another intriguing topic. In some binary systems, it's possible for a neutron star to merge with its companion before it completes its life cycle. This merger could dramatically alter the fate of both stars, leading to unique supernova explosions, unusually massive neutron stars, or even directly forming black holes. Observing pre-supernova mergers would provide new insights into stellar evolution, supernova mechanisms, and the role of mergers in producing exotic remnants. This area of research helps scientists understand the dynamics of close binary systems and the impact of stellar mergers on the life cycle of massive stars. Another captivating area involves strange stars, an exotic hypothesis suggesting that neutron stars could be composed primarily of strangens, particles made of up, down, and strange quarks but grouped in clusters rather than as a quark-gluon plasma. If strange matter is stable, it could create a unique structure for neutron stars, possibly accounting for their high densities and unusual behaviors without requiring a full quark phase. Observing evidence of strange matter would open new doors in particle physics, providing an alternative model for ultradense matter and challenging traditional neutron star composition theories. Neutron stars also allow scientists to investigate Q-balls, hypothetical stable lumps of quark matter stabilized by a scalar field. Q-balls are predicted in some theories of supersymmetry and may accumulate in neutron stars over time, affecting their mass, structure, and emissions. Detecting Q-balls in neutron stars would confirm supersymmetric theories and reveal a stable form of matter beyond the standard model. This research would not only impact astrophysics, but also provide clues about particle physics and the fundamental building blocks of matter. The study of magnetic pair production around neutron stars, especially magnetars, brings us to high-energy particle physics in extreme fields. In the presence of intense magnetic fields, photons can spontaneously convert into electron-positron pairs, creating cascades of particles. This pair production affects the radiation and plasma environment around neutron stars, influencing their emissions and particle behavior. Observing magnetic pair production provides a test for QED predictions about matter-antimatter creation in strong magnetic fields, giving scientists a way to study particle interactions that are difficult to replicate in terrestrial laboratories. The concept of high-spin pulsars reveals new aspects of neutron star dynamics. Pulsars with extremely high rotation rates, spinning hundreds to thousands of times per second, are thought to form through accretion from a companion star in binary systems. These millisecond pulsars challenge our understanding of rotation limits and centrifugal forces in dense objects. Observing high-spin pulsars provides insights into angular momentum transfer, rotational stability, and the effects of rapid spin on neutron star structure. These findings help refine models of stellar evolution and the role of binary systems in transforming stellar remnants. Another area of research is gravitational wave memory in neutron star mergers. After two neutron stars merge, they produce gravitational waves that carry memory of the event, meaning a subtle distortion in space-time persists after the waves have passed. This gravitational wave memory effect could be detected in future gravitational wave observatories, providing unique data on the merger process and space-time's response to intense gravitational events. Observing this memory would confirm predictions from general relativity and reveal details about the merger mechanics, helping scientists understand how space-time behaves in the presence of extreme gravity. Magnetized accretion disks around neutron stars and binary systems represent another intriguing area of study. When a neutron star accretes material from a companion, this material can form a magnetized disk around the neutron star, with particles spiraling inward along magnetic field lines. These accretion disks generate X-rays and other high-energy radiation, providing insights into magnetic field interactions, particle acceleration, and energy release. Studying magnetized accretion disks helps scientists understand how magnetic forces shape accretion dynamics, providing clues about the role of magnetic fields in high-energy astrophysical systems. Neutron stars also offer a natural laboratory for studying parity-violating interactions in strong magnetic fields. In some particle physics models, parity, mirror symmetry, is violated in extreme magnetic fields, leading to asymmetrical particle distributions. Observing these parity-violating effects in neutron stars could provide evidence for new physics, revealing how fundamental symmetries are affected by intense magnetic forces. This research could help scientists refine theories about particle behavior and symmetries in environments far more extreme than those found on Earth. The hypothesis of massive star clusters with embedded neutron stars also expands our understanding of stellar evolution. In some massive star clusters, the dense environment may lead to frequent supernovae, leaving behind numerous neutron stars. These clusters may host unique interactions between neutron stars and other massive stars, leading to stellar mergers, accretion processes, and even new supernovae. Studying such clusters helps scientists understand the life cycles of stars in dense environments and the impact of frequent interactions on neutron star evolution and behavior. Neutron star recoil velocities add a layer to the study of neutron star movements in galaxies. After supernova explosions, neutron stars can be kicked with velocities that propel them through space, sometimes at speeds of hundreds of kilometers per second. These recoil velocities impact the distribution of neutron stars in galaxies and influence their potential to interact with other stars. Observing neutron star velocities helps scientists understand the mechanisms behind supernova explosions, the forces at play in asymmetric supernova events, and how neutron stars populate and move within galaxies. The concept of spin-driven gravitational wave emissions focuses on how neutron stars lose rotational energy over time. As neutron stars spin down, particularly if they have slight asymmetries, they emit gravitational waves. These waves carry information about the star's shape, internal structure, and rotational stability. Detecting spin-driven gravitational waves provides a way to study neutron stars' interiors and angular momentum evolution, offering insights into how these stars change over millions of years. The study of magnetar-induced shock waves is another fascinating area of research. When magnetars experience magnetic reconnection events, they can release energy in the form of shock waves that propagate through their magnetospheres and into surrounding space. These shocks accelerate particles, creating bursts of high-energy radiation detectable from Earth. Observing magnetar-induced shock waves reveals the processes of magnetic field realignment, particle acceleration, and energy release in extreme magnetic fields, providing insights into magnetar flare mechanisms and cosmic particle acceleration. Another emerging field is astroseismology of neutron stars, where scientists analyze the frequency and characteristics of seismic waves within neutron stars. Like seismic waves on Earth, these waves can reveal the internal composition and structure of the star. Studying neutron star seismology provides insights into the star's core properties, crust composition, and any exotic phases of matter within. Astroseismology of neutron stars allows researchers to explore the makeup of these dense objects without needing to observe their interiors directly, advancing our understanding of nuclear physics in extreme environments. The phenomenon of electromagnetic counterparts to gravitational waves in neutron star mergers is also significant. When neutron stars merge, they emit both gravitational waves and electromagnetic radiation, including gamma rays, X-rays, and optical light, known as a kilonova. These counterparts provide complementary data on the merger process, the formation of heavy elements, and the resulting black hole or neutron star remnant. Observing these counterparts allows scientists to study neutron star mergers from multiple perspectives, helping to build a comprehensive picture of these dramatic events. Neutron star mountain formations add yet another layer to the study of gravitational waves. If neutron stars have small mountains or asymmetries on their surfaces, they emit continuous gravitational waves as they rotate. These mountains are only a few millimeters high, but contain immense mass due to the star's density. Observing gravitational waves from these neutron star mountains could reveal details about the star's crustal strength, internal structure, and any deformations caused by magnetic or rotational forces. The concept of binary neutron star and spiral dynamics focuses on how two neutron stars in a binary system interact as they spiral toward each other. Gravitational forces cause the stars to emit energy, leading to orbital decay and an eventual merger. This in-spiral phase emits gravitational waves and allows scientists to study the gravitational interaction between neutron stars in real time. Observing in-spiral dynamics provides insights into the effects of gravity in strong fields, offering precise tests of general relativity and information on the neutron star's masses, radii, and internal properties. Finally, long-term cooling curves of neutron stars provide a way to study their thermal evolution over millions of years. As neutron stars age, they cool through neutrino emissions, photon emissions, and other processes. By measuring the surface temperatures of neutron stars at different stages, scientists can reconstruct their cooling histories and gain insights into their internal composition and energy transport mechanisms. Observing these cooling curves helps refine models of neutron star thermodynamics, providing clues about exotic particles or phases within the star, and revealing how matter behaves as it approaches absolute zero. Each of these advanced topics in neutron star research highlights the versatility of these compact objects as tools for studying extreme physics. Neutron stars continue to offer scientists opportunities to explore the boundaries of knowledge, from quantum field theory and particle interactions to general relativity and stellar evolution. The relentless study of neutron stars advances our understanding of the universe, demonstrating that these stellar remnants hold secrets that bridge the smallest quantum scales with the grandest cosmic phenomena. If you liked the video, then consider clicking on the recommendation and watch our other videos. Be sure to subscribe, and see you on our next interstellar trip.